So he carried out his research activities in the area of speech signal processing at Tata Institute of Fundamental Research for almost 3 decades. He was there. Later, he was a visiting faculty at IIT Guwahati. So starting from the year 2016 to 2020. Currently, he is an adjunct faculty at IIT Dharwad and at NMIMS Mumbai. His primary research interests are in the area of speech recognition, spoken language resources, and its creation. So he has excellent hold on these topics, and he's a hands-on man. And as the age progressed, like he is more oriented towards the practical aspects of building these systems. So then he has extensive knowledge on Spings, HTK, Kaldi toolkits. So he has been working on this since the early 90s, basically. So he also had visited Carnegie Mellon University, and in the year 1998, so many of us would have not been in the domain at all. So in those days, he could build and demonstrate a practical continuous speech recognition system. And even today, he sits and builds the system. So that is his experience and that is his forte. So who other than we can listen to, if at all it comes to building the ASR models. So thanks to Samudra Vijay sir, he has accepted to give a talk on this, and it's always a pleasure to listen to him. Thank you, sir. Over to you, sir.
Thank you. I assume that you can hear me.
Yes, sir. Yes, sir. We can hear you.
Thank you. Okay. Good morning, everyone. So this is the talk is titled Automatic Speech Recognition using Gaussian mixture model along with the hidden mixture model. This is the acoustic model, and there will be various language models. So we are doing speech recognition, that is by the machine, therefore it is called automatic speech recognition. The common word is speech to text. Yesterday you had an excellent overview of the automatic speech recognition by Professor Umesh. He spent a lot of time on giving the basic ideas of the latest technologies that is emerging and that would be more and more relevant to us. And he also cautioned that in some situations, the existing time-tested conventional technology based on hidden Markov model will also be useful. So today we will be focusing our attention on those conventional models, GMM-HMM, hidden Markov model for modeling the temporal aspect of the speech signal. So I'll begin with an introduction to the sequential pattern recognition. Then yesterday, Prasanna sir gave an introduction to the signal processing and various other aspects, a perspective on the entire process of the speech recognition. I'll just quickly run over that so that then onwards we'll go to the modeling part. When you want to do the speech recognition, models of the patterns that you want to recognize become important. We start with the statistical model, distances, and then we move on to the probabilistic models, normal distribution, and advanced versions of the normal distribution or Gaussian distribution called Gaussian mixture model. This is useful for recognizing one pattern, one sound, for example. Next, we will move on to the continuous speech recognition, which is recognition of sequence of sounds or recognition of sequential patterns. And then there we will motivate why hidden Markov model is a useful model for recognition. We'll touch upon the salient aspects of training and testing hidden Markov model. We'll skip over the mathematical details. Then we end that acoustic model part of the talk with touching upon various models based on GMM-HMM that are implemented by the Kaldi toolkit that we have already started using them. Then I will also talk about the language model, because speech is spoken language. Language is there, the constraints on the sound sequence, word sequence, etc. are there. Let us start with the overview of the speech recognition itself. This is a graph from the HTK book. So right now, we use speech to communicate ideas. Right now, I have some thought in my mind. I want to convey it to you so that it enters your brain and it enters your cognitive world. So I choose a language, English. I form a grammatically correct sentence which encodes the information that I want to pass it on to you. So the sequence of symbols or the words, if you wish, are they encode the concept, they contain the concept. And then I order my articulators, my glottis, tongue, lips, and so on, to move in the right position, and lung also, the source of energy, to move in the certain position so that the corresponding spoken language comes out, speech comes out. What comes out is an auditory wave, a sound wave, a pressure wave, which you call it a speech waveform. It's a sound wave, it doesn't have, but in that sound wave, the information that I want to convey is encoded. It contains that, it's not visible, it's not apparent. So, speech waveform encodes the information that I want to convey to you, and the goal of the speech recognition is to recover that sequence of words or symbols of the concept from the speech waveform. Speech waveform encodes the information. The goal of the recognition system is to decode that information. I'm using this word decoding specifically here rather than recognition is because in the Kaldi toolkit, you will see that at the end of the training, you will also do the recognition. They call it as a decoding. Now you know why the word decoding comes. Speech recognition, recognition. Cognition means we already have some idea of the pattern that we want to, that of our interest. And when we hear the sound, when we hear the speech waveform, those sounds get to the front line of our cognitive system, recognition. So that is true in the case of the sound waves. In the case of visual wave, visual pattern, that is also visual recognition. We are talking with the speech recognition of auditory sounds generated by human articulatory system. Is the general block diagram of pattern recognition system. Generally, the information about the patterns is not apparent in the input. In our case, the input is waveform. Therefore, we need to process it, to process the auditory waveform to extract features that will help us to recognize the pattern. In our case, the basic patterns are speech sound, a, e, u, e, ka, 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 ga, cha, ta, pa, so on. So, to recognize, if the computer has to do it, a machine has to do it, then it has to build a model of these patterns, model of the sound patterns. What is a model? Model is a description of the features of the patterns such that we can do some calculation with that. We can do some prediction, we can recognize. So essentially, for as far as we are concerned, it is a mathematical description of the features of the various sound patterns. So we need to fit model. Model fitting is something mathematical description of the phenomena, and we have to estimate the parameters of the model. So that is called a training. So just like when we started learning ABCD, English is not our mother tongue. We started writing A. This is A with a horizontal line. That teacher tells us, and then we learn. This is called supervised learning. So the system also, the computer also has to be taught like that. It has to be given several examples of each of the pattern, and it has to estimate the parameters of the mathematical model. And that is called a training. So in speech recognition implementation, there are two phases. One is training, and there is testing or recognition or decoding. Our goal is to recognize sequence of sounds, or this is a case of a sequential pattern recognition from models. Well, when you want to recognize a letter, for example, written letter A, B, C, D, it is one image. So that is called a static pattern. It doesn't change with respect to time. On the other hand, if a movie is going on, it is a sequence of images. It's called a sequential visual pattern. In case of sound, if I say that is one sound. But if I say I'm talking like now, it is a sequential pattern. Therefore, we need to recognize sequential patterns. The models that we will be training, we'll be talking today, are one is a Gaussian mixture model, GMM. It's useful to recognize individual sounds. On the other hand, if you have a sequence of sounds, like the sounds that I am articulating right now, and it's reaching your ear, then we need a model that modifies a mathematical description of some process which changes with the time, or a sequential pattern. Hidden Markov model becomes useful. We'll talk about it. Well, speech is a sequential signal. Therefore, we need to process the speech waveform not in a single bunch, but in short segments, because in one, let's say this is about 2.3 to 25 seconds of speech data. There are several sounds here. There's one sound here, one nasal here, one vowel here, and so on. Therefore, we take short-time processing, and typically we take short segments of duration 25 milliseconds and shift it by 10 milliseconds. So 1 to 25 millisecond, one speech frame, 10 to 35 millisecond, another speech frame, 20 to 45 millisecond, another speech frame, and so on. So from each of the speech frame, we process it, and we process it to extract features that will help us to recognize the sound patterns. To know that what kind of features we need to do, we need to understand how the speech sounds are produced. And here is a excellent schematic of production of speech sound. The air pressure in the lungs, that is the source of energy. And when our glottis opens and closes, that gives out puffs of air. How many puffs? Actually 140 puffs per second. That is my pitch frequency, 140 hertz. So that sound comes and excites the air cavity in the throat cavity, in my mouth cavity, and sometimes in the nasal cavity also, collectively called vocal cavity. Vocal because it is useful in the generation of the voice sound. And out comes the speech signal. Okay. And yesterday we had a look at what kind of signal processing is useful. Mel frequency capture coefficient is useful. We do the signal processing. We go to the frequency domain because the properties of the different speech sounds are apparent, becomes more clear there. And then we do the Mel scale analysis, and we do the logarithm. This is the frequency nonlinear scaling. This is the amplitude nonlinear scaling, logarithm. And then to do the better decorrelation, we do a discrete cosine transform, which is equivalent to inverse Fourier transform of the symmetric power spectrum. We get the MFCC coefficients. This we already know. So the signal processing, feature extraction, involves taking short segments of speech. For each block of speech is called a speech frame. And for each frame, you do a computation so that you get several MFCC coefficients, the popular one. There are other coefficient features also. Right now, for the time being, we use MFCCs. Caldi also uses MFCCs. How many coefficients are there? There are 13 coefficients. Typically, you see the number here, 13. There can be positive or negative. The 0th coefficient is a measure of the energy, log energy. So, for every feature speech frame, we get 13 values. These 13 values can be considered as a 13-dimensional feature vector. 13 values can be considered a 13-dimensional vector. Since they represent the features of the speech sounds, we call them as feature vector. So, and in addition to the MFCC, we also compute the first and second derivative of the capital trajectory, slope, and delta, double delta. So, but then it becomes 39-dimensional feature vector. Dimensions doesn't matter for the today's talk. All that we need to remember is for each correspond to each speech frame, there is a multi-dimensional feature vector. For the speech frame number 1, let us denote the multi-dimensional feature vector as x1. This should be in bold or an arrow should be there above. For the second frame, x2 vector. And if our speech signal has capital T speech frames, then there will be the last feature vector will be denoted by capital X subscript capital T. What is this capital T? Well, we said that we will do the short time processing and we get one speech frame every 10 milliseconds. Millisecond is 1000th second. Therefore, if there is 1 second of speech, there will be about 100 speech frames. So if you speak Mera Bharat Mahan, it may be 2.5 seconds long, then there will be about 250 speech frames. 250 in that case is the value of the capital T here. So this is called sequence of feature vectors, and that is the outcome of the feature extraction process that is part of the signal processing. At the output of the signal processing, this is a 2.5 second speech signal. Out comes a 250 length long sequence of feature vectors x1 up to xt. Now, they are also called observations in the hidden Markov model terminology. Why? Because what we see the system gets is able to compute is these feature vectors. That is observable. What is not observable, what is not known is the sound that generated this, or sound sequence which generated these feature vectors. So the feature vector sequence is called observation sequence, O1, O2, O capital T. This is just a terminology notation, just get used to that. And what is not known, what we need to identify is the sequence of sounds which generated these observations.
So Swapnil has raised his hand, sir.
Okay.
Yes, sir. In between, I was typing the question. So, am I audible, sir?
Yes, you are audible.
Yeah. So, sir, you have mentioned about 250 length feature vector just now.
Correct.
So, it's the 250 unique numbers, or it is in that there are each value has that MFCC like. So, there are 13 values for each sample.
Each frame.
Huh,
okay. 250 speech frames, 2.5 second long, 250 speech frame. Each speech frame has 13 values. So, and including this delta and double delta, 39 values. So, each frame has 39 values. We consider a 39-dimensional vector. So, if you consider the total number of values, this is 39 into 250.
Sir, how these 13 value came? It is empirical, or how we are deciding this?
It is empirical. You are right. It is empirical. Why 13? Because 13 MFCCs capture about 5 to 6 formats in the speech signal, and for speech recognition, first 5 to 6 formats are sufficient. I'll just introduce the concept of format again. So this is empirical. Empirical means determined by trial and error. They tried 10, 11, 12, 13, 14, 15, 16, and 16. Sometimes for speaker recognition, for example, they take up to 20 MFCCs also. For speech recognition of speech sounds, 13 seem to be ideal. Next question.
Hello, sir. Hello, sir.
Yeah.
There is I think the frame is 25 millisecond and long, every frame. And there is a 10 millisecond of shifting. That's why in 2.5 seconds, there are 250 frames are there. So that means there is a overlap of MFCC coefficient also.
That is right. Yes. You see, look at the frames here in the blue line here. They are overlapping. So the successive MFCC coefficients contain some kind of overlap. There is some overlap in the information they can.
That means in the first frame I got 13 MFCC coefficient, and in second frame from the last there will be 8 or 9 MFCC coefficient will be same.
No. They are not. They are not exact. The sound, the speech segments of this duration, they overlap. Therefore, the 13 coefficients that are coming from the first speech frame contains the information about the 1 millisecond to 25 milliseconds.
Yes.
Whereas the second frame, 13 coefficients contain the information from 10 millisecond to 35 milliseconds. They contain the information, not exactly same values, because property would have changed with respect to time.
Sir, we are taking 10 milliseconds shape because our vocal cord changes its shape within 10 milliseconds. So
no, that is not true, because for women, children, pitch frequency can go as high as 400 hertz. It is 10 again is an empirically determined formula.
Okay.
It should be short enough so that you can track the temporal variation. But if it's too short, then too much computation.
Okay.
Again, something 25. What is the value about it? Nothing. It's just 25 seems to be the duration of the shortest speech sound. It's like that. So 10 millisecond, 25 millisecond, 30 MFCC, these are all not mathematically derived, by practice engineering. Yes.
Okay, thank you, sir.
Next question, please.
Sir, the 13 coefficients are the starting 13 coefficients, or it can be any 13 coefficients of 13?
It is the starting 13 coefficient, because the starting from the first coefficient, sometimes people use, okay. It is the first 13 coefficients because they represent the smooth log power spectrum.
Okay, sir, thank you, sir.
They represent the smooth log power spectrum. These 13 ones represent a smooth version of this log MEL spectrum.
Yes, sir. Sir, in the next slide, you have mentioned slope and curvature, right, sir? Yeah. What do you mean by this curvature parameter, sir?
I will come to the slope and curvature when we after the spectrogram after 5 minutes. Please.
Okay, sir. Yeah, thank you.
This is here explained visually. Next question. I'll wait for 5 seconds. If there are no questions, I'll move on.
Sir, what is the advantage it will come if you take the shift, if you don't take the shift? What is the difference? Frame shift.
Frame shift. Okay.
If you don't take any frame shift, what happens? If you take the frame shift, what kind of advantage it is coming? Like
okay. Suppose you take 25 millisecond and the next frame is 25 to 50. Is that what you are talking?
Yes, sir. Yes, sir.
If you take if the frame shift is equal to frame size, non-overlapping frames,
yes,
there are some windowing effects which I will not talk about it. Windowing gives rise to distortion and so on. So Fourier transform actually is useful for periodic signals, but this is periodic only for short duration. It is called quasi-periodicity. Why? Because there is one sound here, another vowel here, and nasal here, vowel here. So it varies in the time. Therefore, we take short segment. So when you do the short time processing, as is shown here at the title, we need to use what is known as windowing. It has its side effect. Therefore, to minimize the side effect of the windowing operation that is essential for Fourier analysis, we have overlapping windows. That is little detail.
Okay,
we'll skip. Next question. Okay, so signal processing block takes a speech signal and generates a sequence of feature vectors, 250 vectors, each vector of 39 dimensions, 39 values. And in hidden Markov model terminology, we call them observations. This is called observation sequence of length capital T, which is equal to 250. For our purposes, 250. Now, we come to the linguistic aspect. I have been talking about speech sounds and so on. That has been studied very well. In fact, in India, it has been studied very well since ages, thousands of years. Some terminologies. Phone, We know telephone, mobile phone, phone is speech sound, any sound that is used in human speech communication. Phoneme is one type of phone which is language dependent. Let me give an example. Suppose you look at these two Hindi words. I'm assuming that you can read Hindi. Of course, I'll read. Pal versus thal. So the al is common in both the words. It's only the first sound that changes. Pa versus tha. Aspirated pa. So in Hindi, you just change, instead of pal, you put a little bit of extra puff of air, then it becomes thal. But meaning changes. Since meaning changes, we say that pa and pa are two different phonemes in language Hindi. This is true for most of the Indian languages. South Indian languages, some of them do not have this distinction. So pa and pa, for example, are not two different sounds in Tamil, for example. Whereas they are two distinct sounds which has a distinct role to play in meaning, for example, here in Hindi and Indo-Aryan languages. So pa and pa are two distinct phonemes in Hindi, not so in Tamil, not so in English. For the time being, that is good enough. Set of phones is a superset. Phonemes are subsets. They are relevant to a language. So set of phonemes is relevant to language. I think there was something, probably I'll just check. What is the advantage if we take, okay, that is already answered. Let me move on to what are the phonemes in Indian languages? For the sake of example, I will take the Hindi as the language written in Devanagari script. Most of us can see, but even if you are not able to see it, it is written in the English here in the red. In the blue is the Devanagari script, the vowels in the top row and the consonants in the 5x5 matrix and the bottom. So there are about 10 vowels. There could be more, less, what it depends. And there are 5x5 matrix of consonants here. They are called the stop consonants, and there are some 8 other consonants. So totally around 10 plus 25, 35, 35 plus 8, 43 phonemes in Hindi. The number varies. There are nasalized vowels and things like that. So the number of basic sounds in Hindi is 43 to 60 or something. I'll take number 50 because 50 is a nice number. For our calculation, let's take that number of phonemes in the language, in Indian language, is about 50. Let's just take it. So, when we want to recognize speech, we ideally will start recognizing the basic, these 50 phones, and then from that we recognize the words in the language. From the word sequences, we recognize the sentence that was spoken. That is the speech recognition. Any question before we move on? I just introduced 2 slides.
Sir, one question in the chat.
Yeah. Is it the chat box? Okay, I should probably keep the chat box on, but no, that is over. Let's take a care. Okay.
So someone asking, sir, what is the advantage if we take the shift? What happens if we don't take shift?
Yeah, that was written in the script. But if we do not, if we do not take the shift, then the frame remains as it is. No, we want to study the entire signal. What he probably meant is, what if the shift is equal to frame size? That's what his question. I'm sorry, I'm going ahead. Probably what he meant was, the why frame shift could not be 25 milliseconds. It is done. Overlapping frames are intentionally taken to minimize the side effect of windowing that is necessary for short time speech processing, but that is involved signal processing. So I'll leave at that. Any other question before I move on to the
Stone pool Paul open mate.
None close the very good.
can you please repeat the question?
Because you make the one plan.
Sorry, I am not able to hear the question. If there is a question, please type it in there and move on. Okay, now let us go to the concept of spectrogram. This concept was introduced even by Professor Umesh earlier, but I am going to spend little time on that because this helps us to understand why hidden Markov model is necessary, or why hidden Markov model is a useful mathematical description of speech, a sequence of sounds. Okay. Now, when we did the signal processing, what we did was we did a Fourier transform, which means we went to the spectral domain, spectral property. So, what does a spectrum, typical spectrum denote? It says it shows how much energy is there at various frequencies. Now, that is for one frame of 25 milliseconds. But we want to see the spectrum or the spectral property or the frequency domain properties of the different sounds. Then if there are 250 speech frames, there will be 250 such plots to see. That's not convenient. So the signal processing engineers came up with this idea of representing the spectrogram of more than one frame, 250 speech frames. And that is called spectrogram. Gram is to do with similar to the EEG, electroencephalogram, or ECG, electrocardiogram, telegram in good old days, and things like that. Any gram in general is a time variant representation of some signal. So let us look at the time waveform here. Look at the time waveform. There are several ovals here, and probably there is a silence here, and then oval, nasal, and so on. This is actually the word Thiruvananthapuram, spoken by a Bengali person, so he called it, it was a Thiruvananthapuram instead of Thiruvananthapuram, both lamba. Okay, so this is the time waveform. We call it a time waveform. What is on the x-axis is time. The time is denoted in milliseconds. We are used to milliseconds. This is 800 milliseconds. Therefore, this is about a second long. Now time waveform and the amplitude is shown here. It's a digital signal. Therefore, positive amplitude, negative amplitude. Maximum amplitude is 13,000 here. Negative amplitude is minus 16,000. This time waveform, digital. Here, if you look at this vowel, this is a vowel, this is a vowel, we can see because of the higher amplitude. But difficult, this vowel appears similar to this vowel. Therefore, information, the identity of this vowel, whether it is same as this or different, what is this vowel, difficult to figure it out from the time domain. Therefore, we do the frequency analysis. When you do the frequency analysis, we take speech frames, segments of duration per millisecond, and compute a spectrum. So in spectrogram, that spectrum is plotted as a strip, vertical strip. For example, let us look at the spectrum of 25 millisecond duration here. Remember, from here to here is 100 millisecond. Therefore, 25 millisecond is 1/4 of that. That is about this much. So about this much. And there was a burst here, explosion. It is actually Tiruvantha release, and you see something here like a strip here. This is the characteristic of the sound release of Tiruvanthapuram. So now this, so what is on the y-axis? Y-axis is the frequency. You see the hertz here. Hertz is the unit of frequency. What is the frequency range? 0 to 6,000 hertz is plotted here. So in a spectrogram, time is along the x-axis, just like time waveform. All grams are time along the x-axis. But in spectrogram, spectral property or the frequency scale is along the y-axis, and the intensity of, there is more intensity here. If you look at this explosion, Tiruvanthapuram, there is a lot of intensity at around in the region 3,000 to 5,000 hertz. In the region 3,000 to 5,000 hertz, there is a lot of energy that is shown by the color. Red color means very high intensity. Yellow color means medium intensity. Blue color means almost no intensity. So since there was a explosion and this is the sound ta, therefore a lot of intensity will be there around 4000 hertz, 4000 plus or minus 1000 hertz. This location of where the energy is concentrated depends upon ka, cha, ta, ta, pa, it varies. That's a property of this sound. That will be useful for identifying, distinguishing ta from pa and so on. So if you look at the time waveform, it's difficult to figure out what this sound is, but if you go to the frequency domain, you see some properties emerging here. Now let us look at the vowels. This is the word Tiruvananthapuram. There's a ta here, there's a ta here. This ta and this ta are similar because these are the same sound. Okay, but here it is difficult to figure it out. Now let's look at the other sound. E, ra, u, ta, this is N here. This is Tiruvan. Tiruvan. Ta, E, ra, u, a, n. That's the labels of missing. But what you see is that whenever there is a vowel here, high amplitude vowels here, you see some dark red regions, which regions of high intensity. Those are called formants. They actually come out of the resonances. We'll briefly talk about that. But let us assume that, for the time being, let's take that. I don't want to go into signal processing aspect. Let's assume that there are, in the frequency spectrum of a vowel, let us take the vowel E here, Tirua, T, E. There is a peak in the spectrum. There's a lot of energy at around 500 hertz. There's a lot of energy at around 2000 hertz. There is some more energy at around 2800 hertz, and here and so on. So these are high energies. They show up as the peaks in the spectrum. I'll show some spectrum later. And these are called formants. This is called F1. This is F2, second formant or the second peak. F2, third peak or third formant, or F3, F4, F5, etc. It's much more clearer in this Tiruvananthapuram. This is the pa, u, ra, a, m. The a is here. Let's look at the spectrogram with the word a. The F1 is here, first formant frequency. Second formant frequency F2 is here. What is the value of the F2? Around 1300. What is the value of the F3? Around 2000. What is the value of F4? You can look at it. F4, F5, even F6 is there. There are 6 formants showing up in the case of the vowel R in this spectrogram. In the case of the puram, this is a nasal, therefore there is less energy in the higher formant frequency. So what you see is the spectrogram is a visual representation of the speech signal because it displays the frequency domain properties of various speech sounds. Therefore, it is easier to distinguish between different sounds. Therefore, we do a frequency analysis. Frequency analysis has become de facto method of analyzing speech sounds, in general audio sounds. Any questions?
Sir, if we can know frequency of like a particular character, then it is like templates bit SR. Can we build on this?
Exactly. Hey, क्या यार मेरे मुंह से आपने बात छीन ली. There's a Hindi phrase. Oh, good. I like that. That we have to think ahead. Can you do this? Yes, we are going to do exactly that. But before we do that, somebody asked you, what is the slope and curvature or the delta that we talked about here, slope and curvature. Now, it's easy to figure out what is slope and curvature by looking at this spectrogram. This is the word Tiruvananthapuram. Okay, so this is ta, e, ra, u. This vowel from here to here is u. Or in the time domain from here to here is u. If you look at the spectrogram here, you see the second formant here. Second formant. This is the vowel u from here to here. Still, the second formant frequency is varying. You see, it starts around 1600, goes down almost up to 1200. so much variation. It is coming down. In some cases, it is moving up. In some cases, you look at this guy, F4 here of vowel A, it comes down and goes up within one vowel. When we write sound A, let's look at this letter A, it's printed letter, fixed. It doesn't change. Any printer, it will remain like that. But you do the handwriting, you write A, I write A, they slightly differ. Similarly, well, that is one reason. So, although this entire frame duration, this is about 100 milliseconds, you see, 700 to 800. 100 milliseconds, 10 frames of speech belong to one vowel A, still the format sometimes decreases frequency, sometimes increases. It is not random. There's a method to madness, and we are going to utilize that method to do the better speech recognition. It is called phonetic context. I'll come to that. It's useful for why to motivate why hidden Markov model is necessary.
Sir, it is happening actually due to the next phoneme. Next phoneme.
Yeah. I know. We'll come to that. We'll come to that. Please don't jump. Thank you. Yes. No, see, I'm motivating at people. Some people are new to speech, so I'm just starting from the beginning. Thank you. So it is because the next phoneme and previous phonemes, it's called phonetic context. Therefore, I am answering the question, what is the slope and curvature? It is important to measure not just the frequency of one vowel for F4, 3 or F4 of the one vowel, because F4 itself is varying. Therefore, it's better to measure the slope and also curvature. You see, it is changing. This is decreasing and increasing, whereas this is increasing and decreasing. F5 is increasing and decreasing, F4 is decreasing and increasing. Curvatures are different, convex, concave. Therefore, it is useful to measure not only the slope but also the curvature. In fact, you see format here is dropping very rapidly here, and that is a cue that helps us to give determine the identity of this sound as well as the next sound and so on. Okay, I'll move on. Signal processing ho gaya. Now somebody said, can't we use these formats to recognize the sounds? Very good. That's what we are going to do now. We'll recognize individual sounds, vowels. Static pattern recognition. Recognize one sound. That's why I use the word static. So we will do the recognition of vowels using the first two formats. Okay, why do you say first two formats? You see the second format, that is the most dynamic in most cases. And if it is just first two formats, each vowel has two features. Therefore, we can plot each vowel in a two-dimensional surface on a plane. Therefore, we will take the first two format frequencies. Well, we talked about the resonances already. Now, let us. This is the concept of the spectrum, typical spectrum that people use. You see the format frequency of, this is the word IE. You can think it of I am going, I in English word, or the Marathi word IE, which is mother. So if you look at A, that is shown by the red curve, and the first format frequency is around 700 Hertz, and second format frequency is around 1300 Hertz. On the other hand, E, shown by the spectrum of the E is shown by this black curve. The F1, first format frequency is around 300 Hertz, F2 is around 2500 Hertz. So you can see that formats can be used as signatures of the speech sound. We can do the speech recognition. And that is the goal that I'm running slow, the goal. So we can use the F1 and F2 for recognizing vowels. And this can be measured even from the spectrogram. So let's go to the F1 and F2 space. In this graph, F1 is along the x-axis. This is in kilohertz. Therefore, 1.0 kilohertz is 1000 hertz. This is also in kilohertz. So 4.0 is 4000 hertz. And this is plotted in the logarithm scale for the sake of visual illustration. And this is a standard graph that is actually plotted some half a century ago. F1, F2 space of American English vowels. They asked 100 people, children, adult male, adult female, total 100. Each of them who spoke the individual vowels, their F1, F2 was measured and plotted here. And in earlier, we saw that by looking at the spectrum, we can see that E and R can be distinguished because their F1, F2 values are different. Here we can see it is visually. You see that whenever somebody said E, then most of the F1 and F2 are, F1 was around 300 hertz, F2 varied from 2000 hertz to 3500 hertz. Huh? Why does it vary? It's the same sound, why should it vary? It varies because of the concept of resonance. Now, resonance depends upon the size of the vocal tract from the glottis up to the lips, and this head, adults have a big head, and the length of the vocal tract is longer, so wavelength of the resonance is longer, resonance frequencies are lower. Longer the head, frequencies are lower. So male are taller, therefore male adults have a lower resonance frequency, whereas adult females are slightly shorter, therefore their lengths of the vocal tract is longer, resonance frequency is slightly higher. Whereas children, they're short ones, therefore their length is smaller, therefore frequency is higher. So E spoken by children will have the points here. All the data points are here. So these data points at the higher end, higher frequencies belong to children. At the middle one belongs to adult female. This belongs to adult male. So it is dependent on physiology, nothing to do with the gender. Therefore, even if this vowel is E, there is a variation spread. Therefore, we need to use a statistical model. So we cannot say that F1 and F2 of the vowel is this value. No, this is not fixed. It is a spread. Therefore, what we do is but what we see is that different vowels occupy different space in this F1, F2 diagram. Therefore, we can use F1, F2 to recognize sounds. What we'll do is we remember the center of each of these clusters and store it. Now, this is a model. What is a model? This is a kind of statistical model because we compute the average of F1 and average of F2. It's a point in two-dimensional space. Therefore, it's a two-dimensional vector. Generally, due to the letter mu vector, mean vector. It's a two-dimensional vector because there are two features. If it's a 13-dimensional feature vector, then it's a mu vector of 13-dimensional space. That's the difference. So you can compute the mu vector of vowel E, vowel A, kaise, and A, O, U, and so on. So they say there are 10 vowels, there are 10 mu vectors. When somebody speaks a vowel, computer knows how to compute the MFCCs and then pick up the peaks in the spectrum, in the smooth spectrum. MFCCs represent the smooth spectrum. It can pick up these peaks. Therefore, it knows F1 and F2. Then, suppose a data point is, let's say, somewhere here where my cursor is. It finds the distance of this new vector of the test speech whose vowel identity is not known, distance of the x from the mu of this vowel, mu of this vowel, mu of this, and mu of all the vowels, finds out to which cluster center it is closest, and since this data point is closest to the center of the vowel A, long A, we say that system can say that whatever the person has spoken is vowel A. That is the vowel recognition. So we use the Euclidean distance to do the classification. If the test vector is closest to the center of the kth cluster, let's say third cluster, then we assign the test vowel to class number 3, or the distance is lowest, minimum distance classification criteria. But we saw that this assumes that the shape of these classes are circular. It isn't circular, it is elliptical. You can see that it's elliptical. It is a standing ellipse, whereas here it is a sort of sleeping ellipse. Horizontal ellipse, vertical ellipse, this is octagonal. So the variances along F1 is different than the variance along the F2, and in some multi-dimensional space, we not only need to consider the distance, but also the distance should be normalized by the variance along those directions. And sigma square is the variance, sigma is the standard deviation. So we can consider this elliptical shape, that the variance along the one feature and the other feature are different, and use the weighted Euclidean distance. We can do again reclassification using weighted Euclidean distance. Here we use the mu, mean, which is a statistical property, and variance, that is also a statistical property. Therefore, this is a statistical model of recognizing ovals. I'll pause here. Any questions? Quick questions.
Sir, how to plot that F1 versus F2, sir?
Yes, you ask 100 people to speak oval E and use the spectral analysis. You use the MFCCs, or you look at the spectrum and identify the F1 and F2. F1 of I is here, F2 of I is here. How do I know? F1 of I is here. Now let's look at the word. This is A and this is E. Okay, this is A. F1 is here. I can the scale is gone. The F1 is here, F2 is here. You can measure F1 and F2. Programs actually can do that. MFCC does the smoothing, therefore it's easy to pick up. So once you know the F1 and F2, you put a point here. Some other person speaks, a child comes and speaks, F1, F2 will be a point here. What is this point? This point, F1 is 300 hertz and F2 of the child is 3100 hertz. Did I answer your question?
Okay, so this is an empirical based. I mean, there is no tool.
This is not tool based. This is now we are in this tutorial we are talking of concepts. Of course, you will be program can plot it. This is plottable, trivially, computer programs. Right? Yeah.
Sir, actually, like my question was like there will be in one language there will be different dialects, right?
I agree. Therefore, there will be variations. These are the details. I'm right now going at the fundamentals.
Okay.
In a given language, how do you do the speech recognition? So I'm not even gone to speech recognition. I'm still at the oval recognition. Therefore, dialectal variations will be there. You have to take care. Let's start with models. They will go to that later.
Yeah, actually, my concern was how much the equivalent distance will be different from one phone to other phone within the same language when dialect changes. So that I thought.
True. They do vary. Therefore, the F1, F2 based speech recognition system didn't do that well. That was done 50 years ago. Therefore, we are going from statistical model to the next model, which is probabilistic model.
Okay.
In statistical model, what we did was, if the distance is smaller, we assign it, we give a fixed label. Okay. When in probability model, we don't do that. We say that the probability that this sound is A is this. This sound is A is this. Therefore, to do that, in case of statistical model, we used mu and sigma as the parameters of statistical model. Here also we do that, but we also assume some property of the probability distribution. Let's consider the format frequency, second format frequency, F2, because that's very variable. If F2 for oval E, the typical value of the F2, if you look at it, oval E, it varies from 2000 to 3500, around 2,500. Adult speakers between around 2,500. So, if you want to plot a probability distribution, simplest probability distribution is Gaussian distribution, also called normal distribution. It's a probability density function. It's not a probability. The probability density function expression is given here. It has a mean mu and a variance sigma square. Sigma is the standard deviation. When x equal to mu, the probability density function is not probability, it's a probability density function has a peak at x equal to mu, and its spread, how wide it is, depends upon the variance sigma square as the standard deviation. So here for the different probability density functions are shown here with the different means and different standard deviation, just to illustrate the idea of the Gaussian distribution. So if a sample data is given, so let's say oval E is given, then you ask 100 people to speak oval E, you measure the MFCCs or format frequencies, you can compute the mean and standard deviation. Therefore, you can assume that the oval E follows a normal distribution. ellipse shape like this, covariance matrix, it comes into picture, and you can compute the mean and you can compute the variance along both the features, actually covariance matrix, and you can estimate the parameters of the normal distribution, mean and covariance matrix. Actually, it should be covariance matrix because of multiple features. Pause 5 seconds. Okay, I want to introduce the concept of the likelihood here. Likelihood is a kind of probability. It's not the probability, but it is called conditional probability. Because the word likelihood keeps coming everywhere, even in the Kaldi, you will see that. Therefore, let's take that concept. Let us say, let's talk of language Hindi in India. What is the probability that Hindi is spoken if you go anywhere in India? Probably 0.4, 0.5, 0.6, depending on who is asking, but it's around that. Okay? Because 40% of the people speak Hindi or some of these dialects. No, that is the probability that we are talking. It doesn't matter which part of India you go. Okay? You are talking India as a whole. Now, in contrast, you say, you go to Maharashtra and ask, what is the chance that a randomly picked person speaks Hindi? Probably it is 0.2, 20% of these people speak Hindi. Now, you go to next state, Madhya Pradesh, and ask, what is the probability that a randomly chosen person speaks Hindi? Randomly chosen person speaks, a person who is randomly chosen in the state of Madhya Pradesh speaks Hindi, 0.99. So the probability is 0.99 in Madhya Pradesh, probability is 0.2 in Maharashtra. If you add them, it becomes more than 1. You say, "Arey, aisa nahi ho sakta hai." If it is actual probability, some of probability should add up to 1. They all should be positive. It should be between 0 and 1. Some should add up to 1. It doesn't add up to 1 because these are not a priori probabilities, probabilities without the region consideration. These are conditional probabilities because we asked, if you choose a person in Madhya Pradesh state. So we started with if we are in Madhya Pradesh state and we choose a person. Therefore, that if condition is there, then if you ask the probability of somebody speaking Hindi, that is called a conditional probability shown here. The term for that is likelihood. Why it is important? In case of speech recognition, we have around 40 sounds. So what is the probability of F2 being 2000? We can ask for every sound, and then each of the sound will give you some probabilities. You should not add up because they are conditional probabilities or they are likelihoods. Okay, that is the pause for 5 seconds. Janna Vaishnavi, can you mute it, please? Thank you. Okay. I have to move on. I'm running out of time. I'm going very slow. Okay, so you can use, earlier we used the statistical property. We use the classification criteria based on Euclidean distance or weighted distance. It's a classification criteria. Now you can do the similar thing based on the likelihood that we have a model for a green sound class. I talked of Hindi and states. In this particular case, Hindi is similar to what we observed, that is the formant frequency, and different states correspond to 40 or 50 speech sounds in a language. So we fit models for each of the sounds. Let's say there is a sound A, which is denoted by green curve here, whose probability density function, Gaussian distribution function is shown by the green curve here, and there are vowel E, F2 is higher, therefore the mu of the F2 of vowel, second formant frequency of vowel is higher, it is shown here. A point, somebody speaks some vowel, we need to determine whether it is A or E. Suppose the F2 of the vowel is this value, then you see what is the likelihood that it has come from the green curve. That conditional probability of the likelihood is this value. What is the probability, conditional probability that it has come from the blue curve or the vowel E? That is this much, which is higher. Therefore, F2 of this value must have arisen from this curve. So which is the blue curve or the oval E, therefore the unknown sound is oval E. So we can do that kind of classification. Here it is called maximum likelihood classification because whichever class has higher likelihood, we assign the test data to that. That was maximum likelihood. Likelihood is opposite of distance. So in the case of when you talk of the distance, we talked about minimum distance. You see the minimum. So it is minimum distance and maximum likelihood calculation. You will see quite often you see this term maximum likelihood. Okay. Now, what is the difference between maximum likelihood and distance? Let us consider a point which is here. Let me take this. Suppose F1 is 0.700, and F2 is 1000. The point comes here. Does it belong to the A or does it belong to O? There's a problem because it could be the O spoken by a child, higher frequencies, or A spoken by a male adult. We don't know. The F1 and F2 of A spoken by adult is at the lower end of the A ellipse, and F1 and F2 of O call spoken by a child will be at the higher end of the O. Therefore, both can be present here. Therefore, if you measure F1 as 700 and F2 as 1000 hertz, you cannot tell. It could be A spoken by a male adult or O spoken by a child. There's a confusion. Therefore, definite allotment of the sound labels is not a good idea. Therefore, we go to the probabilistic model. That's the first point. That's what we did, probabilistic model. We use the maximum likelihood criteria. But now let us go. What we did was to assume that the probability distribution follows normal distribution or a Gaussian distribution given by this expression. But this expression assumes an elliptical shape in the multidimensional space, which is sort of true here for the oval E. But let us look at the oval A. A is the first sound in our alphabet. If you look at the shape of this cluster A, it is not ellipse. It is bean shaped. Bean, B-E-A-N, like a seed. It is like this and like this. So, since it is not pure ellipse, a normal distribution does not describe the shape of this cluster well. On the other hand, I can describe this cluster as the sum of two ellipses. One ellipse here, like this, slightly vertical. Another ellipse slightly horizontal, shifted to the right. So this bean-shaped cluster can be described as the sum of the two ellipses. And each ellipse can be described by one Gaussian. Therefore, this cluster of A can be described as the sum of two Gaussians. It's also called a mixture of Gaussians. Such a model is called Gaussian mixture model. Let us go to the first one-dimensional example. Suppose our probability distribution shape is like this. It doesn't have a single peak, it has two peaks. If it's a single peak, Gaussian distribution will be green up. If it's a double peak, if the actual shape of the probability distribution function is red curve, solid red curve, then it can be treated as the sum of the green curve and a blue curve. Green curve is modeled by one normal Gaussian distribution with the mu1, standard deviation sigma 1, and the blue one is mu2 and another standard deviation sigma 2. Mu1 is smaller than mu2, and the spread here is higher. Therefore, mu1 would be different than mu2. Sigma 1 could be different. So covariance symmetry could be different. And also, the height of this blue is lower than the height of the green. We add together, we can reproduce the red shape curve. Therefore, the contribution of the blue is about 20%. Contribution of the green is about 80% in construction of the red curve. Those are called weights of the mixtures. There, and the weights are denoted by alpha and 1 minus alpha here, because weights have to be positive and they have to add up to 1. That is the condition of a weighted sum of the likelihood. So a model, we have to describe this curve, red curve with the two multiple peaks, cannot be described by one Gaussian. We use two Gaussians. That is called a Gaussian mixture model with the two mixtures. There are two mean vectors and two covariance matrices and two weights. And you can compute the likelihood of such a model also is given by here. And we can use a Gaussian mixture model to do the maximum likelihood classification. And the Gaussian mixture model, is it necessary? Let us look at that. I showed here something with the artificially red curve, but does it actually happen in case of speech signal? Yes. If you look at the one capital coefficient of even one phone, here is the histogram of the coefficients, plus and minus. You see that there are multiple peaks here. So if this curve histogram is modeled by one Gaussian distribution, it will not be good. On the other hand, you can model this histogram by this curve, which is obtained by adding 10 Gaussians. Therefore, this curve is modeled by a Gaussian mixture model with 10 mixtures. It represents this histogram better than a single Gaussian. So in case of speech recognition, they discovered this. Therefore, they use the Gaussian mixture model. This particular case, Gaussian mixture model can be modeled as, let's say, 3 peaks, just for sake of. So Gaussian mixture model has 3 mixtures, and there are 3 means, mu1, mu2, mu3 vectors, and similarly standard deviations are covariance matrices, and 3 weights. All the weights are positive, and they have to add up to 1. So that completes the Gaussian mixture model. And before I move on, let me see whether there are any questions. Let me just see one more. Yeah, so Gaussian mixture model is shown graphically here. If there is a cluster of some arbitrary shape, it can be modeled as one mixture here, one mixed Gaussian here, one Gaussian here, one Gaussian, mixture of 4 Gaussians, and shown here also. This is Professor Chandrasekhar's plot. So you can fit Gaussian mixture models for 3 classes. This is the entire F1 octave space, but you can fit the Gaussian mixture for class 1, class 2, class 3, and they represent the individual classes better. So even if there's a significant overlap between the classes, Gaussian mixture models help us to do the classification or the class recognition. Okay, this is a time to pause and look at the questions. Is it possible to create own oval chart for new language based on format? Question answer is yes. It has been done for various languages. For Hindi, Dr. S.S. Agrawal did it some 3 decades ago. We also did it in short one. There's a paper on that. You should do that, and that should be part of your phonetic analysis of your language. If you are doing a language like Adi or anything such like that, you should have it. That would be one conference paper. You should do that. And there are lots of languages in India, so that would be one paper. Good. Next question. Repeating the question about format of frequency. Does it represent the peak in the frequency spectrum? It represents the or are there predefined frequency ranges as per human vocal characteristics? No. It represents the peak in the frequency spectrum. Let me just show it again. Let me go back to a typical spectrum. I did show it somewhere. So this is the first peak of the vowel E. This is the second peak of the spectrum, smoothed spectrum of the vowel E. So the peak occurs at frequency 300 Hertz. Therefore, first formant of the vowel E is 300. The second peak in the smooth spectrum occurs at around 2300 Hertz. The peak occurs here. Therefore, it's the second frequency of the second formant is 2300 Hertz. This is the second formant, the first formant. A formant, second formant has a frequency, amplitude, this height along the x-axis, and bandwidth. You see, this is wider, this is narrower, and so on. So formant means peak. Formant frequency means frequency at which the peak occurs. Okay. GMM data shown is 2D data. No, it is GMM for in any dimensional space, right? Okay. In this, let me show GMM. Here, I showed it for unidimensional space. Only one feature along the x-axis. This is again one capsule coefficient for a single dimensional feature vector. Whereas here he shows two features, x1 and x2, two-dimensional features, maybe f1 and f2. You can think of GMM in the 39-dimensional vector space. That is just mass going up. Doesn't matter. So, okay. So it depends on the feature dimensionality of feature vector. Since Mahesh asked, since f1 and f2 are overlapping for different vowels, so GMM is necessary. No, GMM is, well, that overlap is a problem. Therefore, we need probability distribution. Even normal distribution would be all right. Now, normal distribution would be all right if the if these are oval shaped. If they are not oval shaped, as you see in the case of the R, then you need to represent the shape of the R as one ellipse slightly vertical and another ellipse slightly horizontal. Okay? Or look at this. The distribution of one capsule coefficient has multiple peaks. This is just one feature, single dimension feature vector. Still it has multiple peaks, therefore single Gaussian is not good enough. So if the probability distribution has multiple peaks or it is not symmetric, then we should go for Gaussian mixture model. How many mixtures? That's a question. That's a separate question you need to determine on your own. There are mathematical criteria that will help you to determine. How many frames become one phoneme? Well, that depends upon the duration of the phoneme. Let me go back to the spectrogram, because that things become easier. Let me go here. Okay. Let us look. This is the word Tiruvananthapuram here. The tha sound is from here to here. You look at here. That probably its duration is 2 or 3 frames. Whereas oval E is from here to here, about 5 frames. The ra is only 3 frames. Oval A, it begins at 700 millisecond to 800 millisecond, around 10 frames. This is oval A, long A. Yes, so the duration of the phonemes vary. The short E may be 3 frames long, long E may be 10 frames long. So duration of the speech sound determines the number of frames associated with each frame. How many frames becomes one phoneme? Yeah, that depends upon the phoneme. Short phonemes will have fewer frames, long phonemes will have multiple frames.
Sir,
okay. Yeah.
Hello. Sir, for our discussion, we started with one frame, we are finding the parameters. So when we model the phonemes, we will take the one phoneme, we will find the parameters, or one frame we will find the parameters?
One frame.
Okay.
So we do the classification for each of the frames. Let me just sort of 1 minute. So for every frame, we say whether it is A or E or O, etc. And if the vowel is long, there will be 10 frames. Most likely all these 10 frames will be classified as vowel A. There will be occurring 10 times. We merge them together and we say that there's a single A whose duration is 10 frames long. So far we have been doing classification at the frame level, not sequence of frames, not at the phoneme level. Yeah, we are still in the static pattern recognition, one frame at a time. Now we want to move on to the HMM. We want to do the phoneme recognition. We'll come to that.
Sir, then how will this extended vowels, sir, like how will that do then? I mean, how that mixture will be created?
Okay, the Gaussian mixture model is created for every phoneme. Okay. We have 50 phonemes, so there will be 50 Gaussian mixtures, one for each phoneme. So how do you find the Gaussian mixture model? You take several examples of the vowel A. Now, jaw is widely open. A. So you ask several people, you get several thousands, hundreds of thousands of examples of the vowel A. Each A may have 10 frames, and 100 people have spoken. Therefore, there are 1,000 frames, and you find the average of the 1,000 formats. That becomes your mean vector. to find the variance.
Okay. So it is an averaged mean vector.
That's right. Average of all the training examples of that particular phoneme.
Okay. Okay. Yes. Thank you, sir.
Sir,
So
question
we estimate
regarding
the parameters always from the training data. Training data is speech data with its labels. Yeah. Next question.
yes, sir. Regarding vowel chart, sir, you have included the examples of vowel in vowel chart. So I think there are diphthongs also which are being included, sir.
True, true. Yeah, see, I am doing some simple-minded one here. For example, in Hindi, how did it happen? If you ask, a South Indian will say, "Kaise ho gaya?" or something. Kai, because his sound is I. Whereas you ask a North Indian, he says, "Kaise?" Almost. Okay? So these distinctions are, I am not sorry. Right now I'm glossing over all those things because I want to convey the basic idea of pattern. Okay, next question, one question. Yeah, that is Swapnil question I answered, Sanjam question. So we can conclude that to cover the whole speech frame, we can use multiple Gaussians. Yes, one Gaussian mixture per phoneme, that is the better. More Gaussian, it seems better. No, the number of Gaussians depends upon the number of phonemes as far as so far concerned, so-called mono model. Okay. How many Gaussian mixtures are there? Is it equal to the number of phonemes in the language? Correct. In fact, we'll conclude that it will be much more. But right now, yes, let's stick to that simple model. How to select the Gaussians in the Gaussian number of Gaussians in the Gaussian mixture model? There are ways of saying how good the fit to the model is. For example, we did this Kessler coefficient if you fit the Gaussian mixture model. Yeah, here. Should I fit it with the 3 Gaussians or 10 Gaussians? Okay. If it is the 3 Gaussians, okay, fit. If it is with the 10 Gaussians, much better fit. So there are criteria for fitness of the measure, the Bayesian information criteria and so on. That can be, it is to be decided by the engineer. There are some measures that will help him to make the decision, but there is no mathematical formula. In many of these things, it's up to your ingenuity, your knowledge. That's why you're doing practicals, and that's why after doing the practicals, you will become valuable in the industry.
Sir, then to conclude, this is a classification and a fitting problem.
Yes, fitting is a training. In always pattern recognition, there is a training phase. Fitting is estimating the mean and standard deviation covariance matrix in multi-dimensional space. That's right. And classification is recognition or decoding or testing.
So, I mean, to conclude that way, like it is a fitting problem, and to find a best fit among all the fits, to find the best fit is the average one.
For a given phoneme, that is part of the training.
For a given phoneme.
Yes, but during testing, a feature vector comes, and you need to figure out to which class it belongs most, or what is the likelihood that this data point is generated by each of these classes. Find out then you assign this test data to that class whose likelihood, class conditional probability is highest, maximum likelihood criteria.
Okay, so there it has to search. In the decoding, it has to search for that particular.
It has to search, exactly. It has to search because it is the maximum likelihood criteria.
Yeah, so you meant to say there will be some lookup table, it has to search from there, whichever is maximum, then that phone will throw.
Exactly.
Am I right? Okay.
There are 50 phonemes, therefore 50 Gaussian mixture model. You find the 50 likelihoods, condition probabilities, whichever likelihood is highest. If it is E, vowel E, then okay, this person has spoken vowel E. Yes, that is recognition testing.
At phone level, for phone level.
At frame level. Still, I'm still
sorry.
at the frame level.
Yeah.
Sorry.
Okay.
I have not come to phone level at all. Yes.
Okay, sir. Yeah. Thank you, sir.
Okay, I'll give 1 minute break. I'm running extremely slow. I'll give 1 minute break and then we'll recover. Okay, just for us to grab a cup of coffee or something. I actually have a cup of coffee. Let me drink it. Yes, 1 minute break. I'll come back. Okay, let us resume. I know I didn't give probably 1 full minute, but sometimes we need peace of mind. Quickly check whether there's an important WhatsApp message and so on. Because many ideas have come in, it needs time to settle down. So peace of mind, 1 minute, that's very great. Okay. Now, so far we talked about, let me do the 11:20. So far we talked about using the, what are the models that we use? Let me just go back quickly. We are still recognizing one pattern at a time, one speech vector at a time. We are training the models by taking lots of examples of the vowel and put lots of examples of speech frames of the same vowel and fit a model. And during testing, we take one feature vector of 25 millisecond duration, corresponding to millisecond, and then we assign it to one of the 50 phonemes. That is a testing using pattern. And what kind of models did we talk about? That's what we talk. Feature vector, whether it is a signal processing, MFCC vectors, or formats I'm using because it's easy to visualize. Models. What models did we use? We used the statistical model, which used mean vector and sometimes variance. Still statistics, no probability, fixed deterministic classification. Then we said, well, we extended to multi-dimensional case, in which case covariance metric comes and so on. Then we moved on to the probability distribution. We said that there is overlap in the classes. Let us say at this point, we can't tell whether this point here belongs to A spoken by a child or A spoken by an adult. Therefore, we will not make a decision right now that this is A or A, but we will remember the probabilities and later we will use the lexical information and other information and so on. Therefore, we moved on to the probabilistic model. Simplest probability model was a Gaussian distribution, but Gaussian distribution assumes that the bell-shaped curve is a single peak and it is symmetric, but we saw that in two-dimensional case it will be a ellipse, but sometimes it is not ellipse, and even if you see the histogram of a single feature also, it has multiple peaks, it is not symmetric. Therefore, we fitted it with several Gaussians, or collection of Gaussians, or mixture of Gaussians, the Gaussian mixture model. Therefore, and that's where we stop. We are still recognizing one sound. Now we will make the transition to recognizing one word or one sentence. Let's go direct to the recognition of words and so on. What is a word? Word is a sequence of phones. If I say the word Bharat, probability is 0.3 seconds long, there will be 300 feature vectors. So word Bharat is encoded in 300 feature vectors. We, from the analysis of classifying taking the 300 feature vectors, sequence of 300 feature vectors, we need to identify that the word spoken was Bharat. It has 5 sounds, bh, a, r, a, ta. 5 sounds are there. So 300 frames corresponds to 5 sounds, 1 word. We need to recognize sequential pattern. That is the job of the speech recognition. Why can't you do it? Look at the OCR, see printed text does it so easily, but you see that handwritten characters, OCRs do not do that well because there is variation. My R looks slightly different than your R and so on. So the variability is the problem of the errors in speech recognition. There are various kinds of variabilities. I'll quickly run through some of these things and come to the phonetic context. Somebody already pointed out to that, and that motivates us to see the utility or usefulness of hidden Markov model. One, we briefly talked about this. The vowel E is spoken by a male and female speaker. In fact, this I spoke it. My formant frequency was higher than my wife's formant frequency because her head size is smaller. The frequencies are higher. It's the same vowel E in the same phonetic context word pin. There, so the physiology-dependent variations in the phoneme frequencies happen. And when we speak continuously. See, in isolated word, if you want to say the sequence of 3 digits, normally if you want to speak clearly over the phone, then we say 2, 3, 8 with the clear pause, silence between them. But we don't do that. In Harmony, we say 2, 3, 8 like this waveform. This is the energy pattern. But worst thing happens. The word 3 ends with the vowel E. And the next word 8 begins with the vowel E. They join together and it becomes a single E. So this is the kind of problems also happen. These are called Sandhi phenomena. And you may have a fantastic mobile phone. I have an ordinary mobile phone. And the characteristics of the speech collector will also be different. Those are all things that needs to be handled. But there is one variation that is little more systematic. This systematic variation in the properties of the speech sounds can be studied using a spectrogram, can be seen, visualized, is easy to understand using a spectrogram. Therefore, I will refer to this spectrogram. Here is the, what are the words spoken? Tiruvananthapuram. No, he spoke as Tiruvananthapuram. That's the kind of mistakes people make. System has to deal with that. That's okay. Alternate pronunciations will take care of that. Tiruvananthapuram waveform is here at the top. Its duration is around 850 millisecond, about a second. And here is the spectrogram. In this pane, I have shown approximate locations of the different sounds. Ta, I, A, Ra, U, Wa, W, A, N, T, U, U, R, A, M. There, U has occurred twice, once here and once here. Tiruva has U, Puram has U. Let us, these U's in text, they are exactly same. In waveform, there is a U here and there is a U here. They appear similar, but U cannot be distinguished with others, therefore we will go to the frequency domain. Let's look at the spectral domain or the spectrogram spectral property. U here. Let's look at the F2, second format, because that's the most dynamic, easy to understand. The U here, average value is around 1600. What you see? The U, vowel U, starts at this time instant around 140, goes all the way up to 200. It's around 60 millisecond long, 6 frames long. The first frame of U has F2 around 1700. And the sixth frame, last frame of U, has a second format frequency around 1200. It has decreased from 1600 to 1200. Now, therefore, the characteristic format frequency or even the capsule coefficients of a single sound can change within a sound. It is not constant. There is a variation. That's why we resort to statistical property in orange or sound. Firstly, okay, it is decreasing here. Now let us look at the U spoken by the same person, so there is no physiological difference. So, spoken at the same time, therefore it is not the background noise has changed or something, his voice has changed morning from evening or something. Look at the format frequency of U here. It starts as low as 1100 and increases up to around 1300. This U value decreased from 1600 to 1200. This U, spoken by the same person, increased from 1200 to say 1400 or something. Once it decreased, another time it increased. Kya karne ka aisa, this kind of variations. Therefore, slope itself doesn't help us. Characterizing just slope or curvature doesn't help us. But there is a method in this madness variation. This is because the U is followed by a bilabial sound. Wa. Wa is a sound that involves lips, articulate. Wa, wa, wa. Any sounds generally which involves pa, wa, ba, they all have lower formal frequency. This is known by phoneticians. So, since after the U, wa came, the formant decreases. Because a bilabial sound is afterwards, formant is decreasing so that it goes close to the vowel, the consonant W. This is called co-articulation. In this particular case, to the left side of O is P, another bilabial sound. Therefore, the formant frequency by P was low, so it increases. But and here R is on the left side of O, whereas here R is on the right side of O. So in the case of this O, to the left side there was a bilabial sound pa, therefore formant frequency is increasing, whereas in this particular case, to the right side there is a bilabial sound wa, therefore formant frequency is decreasing. Therefore, this behavior, whether it's going up or down, depends upon the next sound and also to some extent on the previous sound. Previous sound, technical term is phone. Therefore, the property of the variation of the characteristic of a sound depends upon the next phone and previous phone. This is called phonetic context. Therefore, if you want to model this vowel O as a single unit, that is not a good thing to do. Okay. Let us take another example. Vowel I is here, another vowel I is here. Again, same story repeats here. Worse. Look at this A. F1 is here, F2 is here, F3 is increasing and steady. F4 initially decreases and increases within the vowel. Slope itself changes, curvature. F5 increases and decreases. Slope again changes, but also curvature also changes. So many things seem to happen again because of the phonetic context. Therefore, if you model this vowel A, all the 10 frames here as a single unit, it's not good. Instead, we should model it as, let us say, 3 units. Middle part of the vowel, which is less influenced by either left phone or the right phone, and the left part of the vowel or the initial part from here to here, that is influenced by the previous sound, and the right part of the vowel or the third part of the vowel, whose characteristics are influenced by the following sound. So it is better to model one sound as 3 units, as not set of 3 units, but sequence of 3 units. Initial part, middle part, final part, or first part, second part, third part. In Markov model terminology, they call it as first state, second state, third state. So each phoneme, each sound is modeled as a sequence of 3 parts or sequence of 3 states, and characteristic of the same vowel in different parts are different. So we can find the mean of the fourth formant frequency, for example, here in the first part, that is mu1 of the state 1 of the same vowel. Average mu here is mu2 of the state 2 of the same vowel A, and mu3 here is the average of the several feature vectors of the third part of the vowel A. This duration is about 10 frames. So it could be possible that this duration is 3 frames, 30 milliseconds, 3 frames. This may be 4, this may be 3. Need not be equal, it can unequal, we don't know. But how do you estimate mu1? There are 3 feature vectors correspond to this. Of this particular utterance A, there are several utterances spoken by several people. Collect all the feature vectors belong to the initial part of all the 100 repetitions. They compute the mean. That is the mean of the normal distribution or Gaussian mixture model of this first part or the first state. Similarly, you do this for the second part of the second state or the third part of the third state. Each state you can fit a normal Gaussian distribution or a Gaussian mixture model. That doesn't matter. That you fit a probabilistic model mean and covariance matrix of vectors. In this particular case, vowel A had 10 vectors. It is a sequence of 10 vectors, vector sequence. Now, instead of modeling it as a sequence of 10 vectors, we model the one oval as a sequence of 3 states: state 1, state 2, state 3. And computer scientists have studied this phenomena in the past, where they, instead of some continuous curve, they broke it into 3 parts, which are within the part it is assumed to be stationary, therefore it is called quasi-stationary. And they have a graphical representation for that. This is called a state diagram. So the F1, F2, F3, F4, 4 formants of one oval R shows this. They will split up into 3 parts, and 3 parts we call it state 1, state 2, state 3. They denote it by state 1, state 2, state 3. And associated with each state, you can compute the mean vector and covariance matrix for the first part. So we can fit a probability model, a Gaussian distribution here for the state 1. For the state 2 middle part, we can fit another Gaussian distribution. For the third part of the state 3, we can fit another Gaussian distribution. You see the F2 varies a lot here, therefore its variance is much higher, correspond to variance of the second part or the first part. So one phoneme is a sequence of states 1, 2, 3. Each state is associated with the probability distribution. And let's assume that the duration of this state is 3 vectors. This is 4, this is 3. How do you represent this duration? Duration could be different. Now, that duration information also has to be encoded in this model, in this diagram. And that duration is encoded in what is known as a transition probability. Let me explain that. The duration of this first state is 3 feature vectors. Therefore, we say that the system first entered the state 1, it entered and emitted feature vector 1, O1. We have 10 feature vectors, O1 to O1, O2, O3 up to O10, because there are 10 frames belonging to this order in this particular case. The system, we say that in the hidden Markov model terminology, we say that the system entered the first state of the oval R and emitted O1, the first feature vector, first MFCC feature vector. 1 is taken care. Then the system made a transition from state 1 back to state 1. That's another way of saying that system stayed in the state 1 for the second time instant, and it explains the second of feature vector O2. And it again stayed for one more time, O3 is explained. But after that, the O4 should go to state 2. It should be associated with the state 2. Then we say that after staying in the state 1 3 times, system makes a transition from state 1 to state 2 and emits 4th feature vector O4. Or then O5, O6, O7, and then O8 has to be emitted by associated with this feature state. Therefore, we say the system makes a transition after the 7th one. Each time is turned to the state 3, and then it explains that O7, O8, O9, O10. So the duration of the different segments or the states is explained by this kind of transition phenomenon. Okay, let's look at the transition phenomenon. It stayed, it came to the state, made emitted O1, made one self transition, emitted O2, then made one more self transition, emitted O3, then it made a transition to state 2. Therefore, when the system was in state 1, it made 2 self transition and 1 transition from state 1 to 2. From this, we can estimate the probability of the self transition from state 1 to state 1 as a 2 by 3. Why? System was in the state 1 3 times, it made 2 self transitions, Therefore, the estimate of the self-transition probability is 2 by 3, whereas the estimation of the probability of the transition from state 1 to state 2 is 1 by 3. It may, out of 3 times, it may transition from 1 to 2 once. And similarly, you can do the similar calculations here. Therefore, you can compute the state transition probabilities for each of the states. In principle, you can make a transition from state 1 to state 3 also. In this particular case, there are 3 states. Therefore, it can make a transition from any state to any state in general. Therefore, we have 9 state transition probabilities. Aij, I and j both varying from 1 to 3. There are 9 values. It can be arranged in a 3 by 3 matrix. And that matrix of transition probability, 3 by 3 matrix of transition probability is collectively denoted by capital A. Capital A is the transition probability matrix, which is a 3 by 3 matrix, which tells the probability of transition from ith state to jth state. Similarly, there are 3 probability distributions associated with the 3 states. The collection of these 3 probability distributions is denoted by capital B. This is called small lowercase b1, lowercase b2, lowercase b3. Collection of these 3 is collectively called capital B. There is another probability called initial probability phi. I said that system came to the state 1, but sometimes people do not articulate clearly, so they articulate only the last part of the phoneme. Then we say that system directly came to state 3. Therefore, system can come either the first phone feature vector may belong to state 1 or state 2 or state 3. That probability is called initial probability denoted by phi 1, phi 2, phi 3. So these are the parameters of the model, a hidden Markov model. So this is a, let me just see, and of course I can not only represent the state by a Gaussian distribution, but also a Gaussian mixture model. When this is called hidden Markov model, I'll come to that soon. When a hidden Markov, the states of the hidden Markov model are modeled by Gaussian mixture, that model is called GMM-HMM. And Umesh sir yesterday showed this slide that there is a state here, there is a hidden Markov model, the modeling one phoneme Y with the 3 states. He showed the self-transition probability as 0.2 here, and probability of transition from state 1 to state 2 as 0.8. And each state is associated with the Gaussian mixture model. You see, like this, there are 3 mixtures here. So this is an example of a Gaussian mixture model associated with the hidden Markov model. So this is where I just want to take a break, because I introduced the essential concept of a hidden Markov model. Why it is hidden Markov model? Because an observation, these 3 density functions or the Gaussian distributions can be overlapping. When they are overlapping, an observation can come from this state or this state or this state. The state, which state a given feature vector is associated is not known to us, because the probability distributions do overlap. And we have seen that in the case of the F1, F2, F3 diagram also, there are always overlap of the distributions. You see here, and things of that kind. So when you given a feature vector, we can compute the probability that it came from this sound and it came from state 2 of this vowel, but we cannot definitely say that it came from state 2 of the vowel R or state 1 of the vowel, same vowel or state 3 of the vowel R. This cannot be determined. This information is not known to us, or it is hidden from us. Therefore, such a model is called hidden Markov model. Whenever a probability distribution is associated with the state, it is called a hidden Markov model. Why the term Markov? I'll come to that later. Let me pause here and ask questions.
So how do we train HMM? Like
Yes, next. Now just introduce why HMM is useful. That's all. HMM is useful because to represent the phonetic context very well. A sequence, although this entire thing should be one phoneme, it should have been uniform, it should have been a straight line, the trajectories vary or go up and down. Therefore, it's better to treat this one vowel as a sequence of 3 parts, and hidden Markov model trains it very well. Markov model trains it well, but since there are statistical variations, we use hidden Markov model. The parameters of the hidden Markov model are these: transient probability matrix, and the parameters of these 3 distributions, mean and covariance matrix of the 3 distributions, collectively known as capital B, and the initial probability is 5. How do you train it? Next topic after 1 minute break.
Hello. Sir, suppose first phoneme it takes suppose 7 frames, then first 7 frames it will be in the first state, 8th frame will go to the second state.
No. Let us say, let me understand your question. Let us say, let's look at the vowel R here. Okay, this duration is 7. Yes. The R here, this duration is only 7. Sorry, I missed it. The duration of this R is 10 frames. Can you see here? 700 to 800. 10 frames. The R spoken by the same person at the same in the same word, duration is, let us say, 7 frames. Now, what you do is take the 7 frames of A, split up into 3 parts. How to split up? That's part of the training. Let's say 2, 3, 2. Sort of equal proportion. So the 7 frames of this vowel R is split up into 3 parts. First 2 frames are given to the state 1 of R. Next 3 frames are given to state 2 of R. Next 2 are given to the state 3 of R. Whereas here, the duration of the same vowel R, but another instance, is 10 frames. So we give 3 frames to the first 3 frames to the state 1, next 4 frames to the state 2, next 3 frames to the state 3. Now, how do you estimate the mean of the state 1? We take 2 frames from the first vowel R and 3 initial frames of the next vowel R. Totally we have 5 frames, all belonging to the first part of the vowel R, first state. Now we compute mean and covariance matrix. Right now we have only 2 instances of R. In training data there may be thousands of instances of R. You, for each R, you split up into 3 parts, collect all the feature vectors of the first part, compute the mean. That is the mean of the normal distribution representing the first state.
Yes, sir. That means one phoneme we are with the 3 state we are representing.
Every phoneme is represented by 3 states, and the phoneme must have been spoken several times. We use the data of several repetitions of phoneme to estimate the parameters of the normal distribution. Correct.
Thank you, sir.
Sir, in the slide you showed vector state and a sequence state, right? And
in the slide, yeah, I can't hear you.
In the next slide, sir.
1 minute. Yeah.
Vector sequence and state sequence. Why state sequence is discontinuous? I mean, some sort of step, and vector sequence is continuous. Can you?
Yeah. Let me say, even vector sequence is not continuous. There is 10 frames here. There is if you look at the F4 value, there is 1 value here, 1 value here, 1 value. There are 3 points here. There are actually a sequence of 10 points here. I drew it continuously for the sake of visual representation. So it's a sequence of 10 points. I called it a vector sequence because it's a 4-dimensional vector, 4 format sequence. Actually, there are 10 vectors here. Now there are 3 states. It's a sequence of 10 vectors. This is a sequence of 3 states.
Okay, sir. Yeah, got it. Thank you.
It's not curve. I know.
Okay.
Sir, I have a question. Yeah, so for the first stage of a phone, we take mean and standard deviation of the formant frequency or the MFCC dimensions?
That is up to you. In my old days, when I was 4 decades old, we used the formats because MFCC had not yet come. But now MFCC is better. We know that. Therefore, we take the average of the MFCC, which is better.
So that means it will be 39 dimension GM.
Exactly. We are in a 30-dimensional feature vector space, and we say multinomial, multivariate, 39 variate. Yes.
Yeah. And so
GMM, Gaussian, whatever.
Thank you. So second question is, you said we collect all the training data, but how is it possible to manually make boundaries of stage 1, stage 2? So
we don't even know the boundaries of phonemes. So forget about it. So that is the part of the training. I'm not going to the details of that. The training process is an iterative process. What it does is, maybe I'll come to that later because I may spend 2 minutes on that. Quickly, yeah, later.
Thank you. Thank you.
Sir, actually, I have one question.
Yes, Kishore.
Yeah, actually, there is a lot of correlation between the frames, right, in speech. So the symbols which are emitted, the symbols which are emitted by a state in HMM, between those symbols, we'll be assuming some independence, right?
Yes, I'll come to that in the next 2 minutes. Yes, we are assuming independence. Yeah, it's an assumption. Therefore, HMM is not that great. That's why we go to the DNN and so on. Yes.
Okay.
It is already 11:52, which is I took 2/3 of. What we need to do is to take a break because this is a good time to take a break because now we are going to the little bit of mathematics of usage of the HMM, training in HMM and testing in HMM. I'm going to skip the maths, almost most of it because but still some symbols will come. Some symbols like this will come. Therefore, we'll take 5 minutes break. On my clock, it is 11:53. We'll come back at 11:58 and resume from there.
Last question. I mean, to conclude this from last break to previous break. So what we have done is we have covered that GMM part. GMM is for identifying phones, and to concatenate phones together, we are using HMM via 3-state modeling. That's it, sir. So that is a
Yes, we want, because to take care of the systematic variation due to phonetic context, we saw here, we are going to model it by HMM. This is the motivation for HMM. How do you actually do the training and testing? We'll talk little later.
Yeah, so the motivation has been drawn towards GMM, HMM.
Yes.
Okay, sir. Yeah. Thank you, sir.
Vaishnavi raised a hand, sir.
Vaishnavi raised a hand. Please unmute and speak. Okay, I think she already answered. So let's take the break. So it is 55. So at 12 noon, we'll restart. 5 minutes break. Okay, I am back. We still have 2 minutes. Meanwhile, if somebody has any queries, you can ask.
Sir, previously you said that we will divide the state into states like 2 frames for one state, 3 frames for second, and 2 frames for the third. So how do we decide these which frames will go to which state?
We don't know. So simplest assumption that we can make is, to begin with, that all the 3 parts would have equal number of frames.
Okay.
And obviously they have to be integers. So just push them equal.
So this has to be done for each
Segment, each phoneme in entire sequence. Yes.
Okay. Okay.
Entire sentence.
Okay. And it has to be then that probability will be probability curve will be calculated
Later. So I am going to talk about a specific example where one sentence is, let me come to that. Okay, but to begin with, we assume that they are all equal durations. So we can estimate the mean and standard deviation. So the capital B's can be estimated. And from the B's, we can also have an initial value of the transition probabilities, because suppose it stays here, suppose the duration of this part is 3 frames, then the initial value of the A11 will be 2 by 3, and from 1 to 2 will be 1 by 3. That's the beginning value. So we always start with the approximate values of these parameters A, B, and pi, and then using the training data, we improve these parameter estimates. It's an iterative algorithm for training, learning. We will just illustrate that. I will not go to the mathematics, but at least I'll give you the key idea.
Okay, sir. Thank you.
Good. It is 12 noon, so let us resume. So we were motivated. I took this spectrogram. This is a real speech that was spoken by my colleague Anil Dasen, and we saw this is not artificial simulated. Actual speech spectrogram shows the need for treating one phoneme as a sequence of subparts. In here Markov model, they are called states, and each state is associated with a probability distribution, which will be normal Gaussian distribution or Gaussian mixture model, it doesn't matter. And also the information about the duration is encoded in the transition probability matrix, that is A. In this case, there are 3 states, therefore capital A will be 3 by 3 matrix. Okay. And pi is the initial probability. What is the chance that the first feature vector of this phoneme is associated with the first part of the vowel, or second part of the vowel, or third part of the vowel? Pi 1, pi 2, pi 3. In general, pi 1 will be large. Okay. We talk of GMM, we talk GMM-HMM. Now we need go into a little bit of mathematics. So we had a 5-minute break. Let's talk about the probability. These are probabilistic models. Let's revise for 3 minutes, revise some ideas about the probability. Probability of events, 2 events. Let's consider 2 events, capital A and capital B. What is the probability that event A has occurred and event B has occurred? Order doesn't matter, but both have occurred. So this is called joint probability of event A and B. Probability of A and B can be written in terms of the conditional probability and the so-called a priori probability. This a priori probability is like, what is the chance that if I pick somebody in India who is speaking Hindi, his probability is 0.4. Whereas this first part is called the conditional probability. It says that suppose I go to Madhya Pradesh and ask what is the chance that he speaks Hindi, it will be 0.9. Whereas if I go to Maharashtra, then capital B is then Maharashtra. In that condition, if I go to Maharashtra, what is the probability that he speaks Hindi? Probability maybe 0.2 or something. You go to Tamil Nadu, maybe 0.05 or something. So this is called conditional probability, which has, so this says that B has already occurred. Then what is the probability that A has occurred? I have gone to the state of Maharashtra, and what is the chance that a random person in that state speaks Hindi? It is called conditional probability. A given B. This vertical bar is read as B. Now, probability of both have, A and B have occurred. Initially, I went to Maharashtra, therefore I can estimate its probability. What is the probability that I went to Maharashtra, Tamil Nadu, or Arunachal Pradesh? And then, having gone to Arunachal Pradesh, what percentage of people will speak Hindi? And that's the kind of question that I have. Or, in this case, I have gone to Arunachal Pradesh and I asked find out the probability of Hindi speaking in Arunachal. Whereas here I can do the other way around, which is I ask first I ask the question of Hindi, and then Hindi is spoken by in Arunachal Pradesh. So the order doesn't matter. We both have to occur. Whether A occurred first or B occurred first, it doesn't matter in the case of the mass voice which is concerned. Therefore, this is equivalent to this. So we can rearrange this equation. Let us assume that probability of B is not equal to 0. So you divide this equation by probability of B, we get this equation. Now notice, this is a conditional probability here. There is another conditional probability in the numerator here. This is the regular probability, so-called a priori probability. This is another probability, a priori probability. Now, B is a state in India. Okay. Now, let us look at that. The entire nation of India, Bharat, is divided into 28 states and some about 10 union territories. Let's just consider states. So, the B consists of several. So this is wrong, the other way around. B consists of AIs, therefore B is the nation and A are the states. So, if you look at the Bharat map, there are 28 states. 28 states are mutually exclusive, and a union of 28 states is Bharat. So, similarly, let us consider the entire nation is sample space, and if the sample space is divided into several states, AIs, collection of AIs are mutually exclusive, and union of AI is the sample space. Then there is a theorem of total probability. This is in 12th standard maths textbook. Probability of B can be written as the sum of these kind of product of conditional probability and the AIs. So this is given here. So I'll just take it. You go and refresh your 12th standard probability. And probability of B can be written in terms of conditional probabilities. This is called a likelihood, and a priori probability of A. Now, there's a P of B here. For this P of B, I'll substitute this expression and I get this. Probability of A given B is here. Probability of B, numerator I have not changed. Denominator I have substituted this. This expression is called Bayes rule. A person called Bayes, that his name is Bayes, his rule, or sometimes people also call it Bayes theorem, says that a conditional probability of this type can be expressed in terms of these type. Why is it useful? Okay, in our case, B is our observation. Formant frequency is 2000. That's the observation. Formant frequency of this particular feature speech frame is 2000. What is the probability that it belongs to the vowel E? Or what is the probability that it belongs to the vowel A? So A keeps on varying, but what we want to know is, we have observed second Formant frequency at 2000. We want to compute the likelihood that it is generated by the vowel E or U. So you can compute these 50 probabilities, and whichever of the 50 conditional probabilities highest, we assign that speech frame to that class, that phoneme. This is the maximum likelihood criterion that we use. So B is the observation, A is the class label. There are 50 class labels, in our case 50. But that is difficult to find. There is but it can be computed like this. What is that? Let us look at this term, P of A. What is P of A? Probability of different classes. Well, you collect a lot of text data, and we know that vowels occur much more frequently than consonants. Therefore, probabilities of vowels will be higher. But it can be estimated if we have a large amount of data. We can estimate it. Therefore, probability, a priori probability of different sounds can be estimated. Probability of A may be 0.05. Probability of a rare sound such as Gha may be 0.001. But it can be estimated. So these quantities are easy to estimate. Now let us look at the other quantity. Probability of B given here. B is formant frequency is 2000. Given that the vowel is, this phone is vowel E. Now this is given by our Gaussian mixture model correspond to each class. Because we know the class. Given the class identity, we can compute the probability of the F1 or F2 or F3, which is given here. So this is the normal distribution. So this first part of the vowel. So various values, formant frequencies are given, and their conditional probabilities can be estimated. This is called likelihood. Conditional probability is highest when the formant frequency is close to the mean value of the cluster and smaller either side. Therefore, if we can estimate the parameters of this Gaussian associated with each of the states or each of the phones, then we know this quantity. This is the a priori probability of the individual sounds. This is the probability of various features. Formant frequency, probability of the formant frequency given the class label. This can be done for each of the 50 phonemes. Therefore, this can be computed if we have a trained HMM. Therefore, this is known in case of a trained HMM, and these terms in the denominator are essentially these. Therefore, this can be computed. Therefore, the probability of the vowel E given that the formant frequency 2000 can be computed, and we can do the maximum likelihood criterion based classification. This is the essence of probability based classification. This is the conditional likelihood that we want to compute, and that can be indirectly computed by the model associated with each phoneme and the a priori probability of the phoneme given a large amount of text data. Any questions here? Quick questions. Okay,
so
fine.
instead of formats, can we consider vector?
Of course, yeah. I'm using format because visually for me it is easier to visualize in the format. It is actually a 39-dimensional feature vector. Okay. Multi-dimensional. That's always there. I'm just using format because it's easier. That's visual. Fine. Another thing that we will talk about is to do with the conditional probability itself. The probability of, okay, now let us say one vowel A in our case, was 10 frames long. There were 10 feature vectors. Let me call it O1, O2, O3, O10. What I'm interested in is, what is the probability that these 10 feature vectors belong to the vowel A? So the feature vectors, let me denote A1, A2, A3, A10. What is the probability of all these 10 feature vectors occur in that order I want to compute? This is a joint probability of n events. I can compute this joint probability as probability the first n minus events have been occurred. What is the probability of the last event, nth event occurs? Is the probability of nth event occurs given that the previous n minus 1 events have occurred. That's the condition probability, and multiplied by the probability of the joint probability of the previous n-1 event. This is a generalization of this expression. Here we had A and B, just two events. We just wrote like this. Now you can generalize it to n events. You consider these events as the second event, then it is A given B, B is this. And so you can use the chain rule in probability to expand even this term recursively, recursion. Probability of this can be written like this again. You see, probability of n-1 given the previous ones, a1 to an-2, and the a priori probability of a1 to a1-2, and so on. So you can continue to do that, and there will be a long sequence. Therefore, I showed it as an ellipsis. Now, suppose we make an assumption that all these events are independent of each other, in which case the conditional probability is this: an does not, since it doesn't depend upon this, this expression becomes just probability of an. In other words, this conditional probability becomes the a priori probability. That's it. It doesn't depend. This is an assumption that we make, and it simplifies the computations. We make that assumption in hidden Markov model. What is the assumption that we make? That oval A, in my case, Puram A, had 10 feature vectors. The probability of the 10 feature vectors occurring in a sequence can be approximated as the probability of each of the individual feature vectors occurring, by making an assumption that the first frame, the feature vector of the first frame does not depend upon the feature vector of the second frame, and so on. We know that it isn't, because they are overlapping frames. But we make this assumption so that we can do the computation easily. Okay. Okay. So that is the math that we need to learn. One is that the base rule, that an observation is given, a feature vector is given, you want to compute the probability that it belongs to class A1 or first phoneme, second phoneme, and so on. So if you know how to compute the likelihood of the feature vector belong to one class, we can do it for other classes, and that can be done using the a priori probability of each of the classes and the probability distribution associated with each class. Whether it is class or state, that doesn't matter, but the same concept continues. Second is, we make an assumption that the probability of a sequence of feature vectors can be approximated as the product of the individual probabilities by making an assumption that observation vectors are independent. Feature vectors of successive frames or any frames are independent, which is not right, but we do for the sake of computation convenience. 10 seconds pause. Okay, hidden Markov model, we have already seen that. The parameters of the hidden Markov model is transition probability matrix. If there are 3 states, it will be 3 by 3 matrix. In general, even in Kaldi, that's what we use. Yesterday, somebody asked, silence has 5 frames. Well, 5 states, it can be. It depends upon the need for how much detail you need to model that particular phoneme. In general, we model each phoneme as a sequence of 3 states. Capital B is the set of 3 distributions, probability distributions, so the 3 states. If there are 5 states, there will be 5 probability distributions. Collection of these probability distributions is denoted by capital B. This is called small b1. This is called small b2. This is called small b3. And pi is the initial probability that the first observation is associated with the state 1 or state 2 or state 3. Pi 1 plus pi 2 plus pi 3 should be equal to 1. So these are the parameters. Now we need to do the training. We need to estimate the parameters. Well, so far I talked of states and things like that in a complex manner. Yesterday, Professor Umi showed this slide. I just took a screen grab and he talked of the states. These are the observations, whether it is sunny, whether it is raining, therefore you need umbrella, or whether it is cloudy. This is something that is visible. What we need to infer is whether there is a high pressure or low pressure weather condition. And you see the transition probabilities from high to low is 0.4, low to high is 0.7. Self-transition probability of the high state is 0.3. Self-transition probability of the low state to itself is 0.6. So from the low, you can either stay itself with probability 0.6, or you can make a transition to other state with 0.4 probability. These two have to add up. These rules are there. And the initial probabilities, pi1 is 0.7. In general, it is warm, at least in Mumbai, where I stay. And low is probability that it is a low pressure situation is 0.3, because low pressure means it is likely to rain. So it rains in 3 months of the 12 years, therefore probability is around 1. Okay. So this is an example of a hidden Markov model applied to a practical situation. Whereas in this case, high pressure and low pressure are two states. In our case, these sounds are states. The phonemes, I, I, and so on. Okay? So if the sentence is, it's fun to recognize speech, this is a sequence of phonemes, and these are the things that we need to infer. These are the states which is not known to us, but what is known to us is observations, which is the speech waveform, from which we get our Mera Bharat Mahan. If it is Mera Bharat Mahan, there will be 300 feature vectors. So 300 feature vectors are known. We need to find out the corresponding phoneme sequence. This is speech recognition. The phoneme sequence is not known to us. Feature vectors are known to us, and hidden Markov model is a mathematical description of such a phenomena. Given the feature vectors, we want to infer, we want to output the sequence of phonemes. And our goal is to find the most likely, see the word likely comes, condition property. Our goal in hidden Markov model is to find the most likely sequence of phonemes for a given observation speech. For a given feature vector sequence, find out the most likely. State sequence. Label sequence is similar to the state sequence. Any question? Because this is a very nice diagram. I'm just copying it. Of course, source is somewhere else. Yeah. So the states could be phonemes or even alphabet. When you talk of wave to wave, just straight letters come, but we start with the phoneme. Let's say 54. Now, so we looked at the hidden Markov model. The parameters are A, B, and pi. So let's state it explicitly. How do you describe HMM? You first have to tell how many number of states are there. In this particular case, there are 2 states. These are hidden states. In this case, there are 3 states. Therefore, capital N is equal to 3 in the case of the speech recognition generally. In case of silence, it could be 5 states. So capital N is normally. And then you denote each state by Q1, Q2, Q3. This is the Q is the symbol for the state. That's the convention. So if there are 3 states, the first state is denoted by Q1, second state is denoted by Q2, third state is denoted by Q3. Capital N is 3. Now, associated with each state, there is a probability distribution. So, which we saw here. So, the first state, there is a probability distribution. This is called small b1. This is the second state. The probability distribution small b2. Third state, probability distribution small b3. There are 3 states. Therefore, there are a set of probability distributions bj. J is the index given to the state. The probability distributions, whereas Q1, Q2 are denoted the states. Probability distributions are associated with the states. Therefore, there are 2 symbols. Q for the states, B for the probability distribution associated with the state. How many distributions are there? There are 3 distributions because there are 3 states. State transition probability matrix denoted by Aij. It is the probability of making a transition from ith state to jth state. It's a matrix, and so the probability is condition probability. Given here, say n by n square matrix, and it need not be symmetric. It isn't symmetric. Pi initial state distribution, pi 1, pi 2, pi 3. We saw the pi 1, pi 2 here. The initial probability of the high pressure is 0.7. Initial probability of the low pressure rainy season is 0.5. So this is pi 1 and pi 2 because there are only 2 states. In case of speech phoneme, there are pi 1, pi 2, pi 3. The entire model is characterized by capital A, state transition probability matrix, set of probability distributions associated with the models, which is here, and the pi. This collectively is denoted by this set lambda. Lambda is a set of parameters A, B, pi, which describes an HMM. Any question? No. Yes, Vaishnavi has raised a hand. Unless yeah, please mute. Thank you. Yeah. Okay. Please ask a question, General.
Sir, can we use normal distribution also, sir, instead of this one, sir?
Yeah, normal distribution is Gaussian distribution. We can use Gaussian distribution. Okay, but Gaussian distribution is not good enough. Therefore, we go to the Gaussian mixture model. Yeah. Normal distribution is same as Gaussian distribution. Correct.
Okay, sir. Thank you, sir.
Now, we make some assumptions. So I'm not going to the math part, but at least assumptions are important. It's good to know the assumption. Assumption is, it makes what is known as a Markovian assumption, which says that finite history. Okay, I'll first show it here. No, this is difficult. Let's take the 3 statements. Then, what is the probability that I make a transition to state 1? Suppose I am in state 1. Let's consider state 2. Suppose I am in state 2 at this time instant. The next time is, when you talk of time instant, it is 10 milliseconds every frame. The first, at this time instant, I am in state 2. In the next time instant, whether I will stay in state 2 or whether I will go into state 3 or any other state, depends only on the identity of the state where I am in right now. It doesn't depend upon what was the state at the previous time instant or previous time instant and so on. I just forget the history. So, if I want to know where I will be in the next time instant, information about the state of the current time instant is good enough. One piece of information is good enough to make the prediction for the next time instant. Or the history is one time duration long. It is called a first order Markovian model. A Russian scientist called Markov studied this kind of models nearly 2 centuries ago, 19th century, late 19th. So that's why it's called a Markovian assumption. Markovian assumption says that it doesn't depend upon what all I did in the past. It's just what I'm going to do next, what state I am going to, system is going to, depends only on the current state, one finite history. Therefore, it doesn't depend upon past, lots of past history, only on one history. That's called first model. Assumption, finite history, first order means only one piece of information. In fact, you can talk of second order, third order, etc. Math becomes complicated, so we stick to this. It's an assumption. It's not correct in real case, but we make the assumption, otherwise math becomes complicated. Second assumption is stationary. You know what is station? Railway station, railway comes and stops there. When it stops there, it doesn't move. Stationarity means nothing changes with the time. So if the average, if you let's say vowel R, its mean of the distribution is 22,000 hertz for formant frequency, that mean does not change with respect to time. That is, when I say Tiruvananthapuram, when I say initially or later, my model parameter doesn't change with respect to time, whether it is today, tomorrow, or somebody else, things like that. Therefore, we assume that all the parameters do not change with respect to time. Therefore, parameters such as age doesn't change with respect to time, bj, no parameter changes with respect to time. That is also not right, because we know that even though we think that the first three feature vectors are modeled by one distribution with the same mean, but you see third format, it is increasing. It does change, but we have to make this assumption of stationarity, that it is stationary, it doesn't, mean values do not change for a short duration, then it changes because it is modeled by another distribution, then it changes, it remains constant for 4 frames, then it again changes. So it is stopped constant for some time, changes constant for some time. It's like a railway station, railway moving to a station, waits for 2 minutes, constant, then moves for another minute, goes to another station, stop, and things like that. So this is called quasi-stationarity. This assumption is called quasi-stationarity. It doesn't change with this time for short duration. That's a quasi-stationarity. It has some, it is not right, it has some side effect, but we will ignore that. Okay, continue. Third, output independent assumption. Somebody pointed out that the successive frames are overlapping. Therefore, in fact, one speech sample may fall into 3 frames because 10 millisecond frame shift, 25 millisecond frame duration. Therefore, the successive feature vectors are not independent. They are related. We know that. But we have to make this assumption that the successive observations or feature vectors, MFCC feature vectors, are independent. We make that assumption. So this is called output independence assumption, and we talked of the related mass just now here. That if the sequence of observations, their probability, joint probability is just taken as the product of the individual probabilities, assuming that the observations are independent. This is the observation in the output independence assumption. It's called output because in the linear Markov model, observations are output of the states. That's the terminology. States emit this observation. That is the vowel, first state of the vowel A emits 3 feature vectors. Emit, throwing it out. So that's why it's the output wording. So that's the terminology. Let's get used to that. English. Okay. So there are 3 assumptions here. Before I move on, I will not go into the maths of the thing. Before I move on, any questions? I'll wait for 10 seconds. Okay. So we make 3 assumptions. Now we'll come to the usage of the HMM. We have not yet trained it. We said what HMM is here. We said we will make some assumptions so that our computation becomes easier. How to train the system, how to use the system. We have not yet talked. Now let us give a hint on how to make these changes. Okay. How to train the system and how to use the system for recognition. First, let us make an assumption. Let's talk of the testing first. It's easier, maths-wise it's easier. Let's assume that we have 50 phonemes and we have 50 HMMs, and we want to see a few vectors. Does it belong to vowel A, E, Ka, Ta, and so on? So a sequence of observations are given. Let's say Mera Bharat Mahan, which is 2.5 seconds long. So therefore there are 250 feature vectors. Capital T is 250. And we have a model of various 50 phonemes. We want to say, for the time being, we'll take capital T as 10 feature vectors. We want to check whether these 10 feature vectors belong to vowel A, E, or U, and so on. So we have 50 models. We need to find out to which phoneme does these 10 feature vectors belong. We use the maximum likelihood criterion. So we need to compute the probability of these 10 feature vectors belong to the model of A, similarly belong to the model of E, and so on. Find 50 like condition likelihoods, that is the likelihood of the model lambda generating the observation sequence, and find out which is the highest. And then we say that this sequence of 10 feature vectors belongs to this problem. So this assumes that we already have trained models for 50. So this is one way of doing the recognition. Of course, this is called forward algorithm, which uses recursion for considering frequency and things like that. So the maximum likelihood criterion is given here. In this particular, there are only 2 models. In our case, 54. Now, let us assume that this observation sequence is 250 vectors long. I said some Mera Bharat Mahan or something long sentence. Then I need to know which phoneme sequence is the output of such a decoding or recognition, and what are the word sequences, what are the phoneme sequences, and where are the boundaries of this phoneme. I need to find out. So given an observation sequence of length 250, I need to find out the sequence of phonemes that match this observation sequence best. A sequence of phonemes is which is given by example of sequence of phoneme is given here. This is the sentence sequence of words, and the sequence of the words corresponds to sequence of these phonemes. I want to output this phoneme, not only output these phonemes, their boundaries, and the boundaries of the words and so on. So I need to know either the sequence of words, there are 1, 2, 3, 4, 5 words, and several phonemes. I want to output this and their boundaries, and that is correspond to a sequence of states of these phonemes, and that there is an efficient way of computing it. It is called Viterbi algorithm. The goal of the Viterbi algorithm is to derive the optimal word sequence or optimal phone sequence corresponding to a sequence of feature vectors. Viterbi algorithm makes it is similar to this, but computation is simpler because it makes some assumption called dynamic programming. We'll not talk about that. So these two are useful when you have a trained model. But what about the training? How do you train the model? How do you estimate the capital A, capital B, probability distributions, etc. from the training data? That is the training part. And there is another iterative algorithm. It is called a forward-backward algorithm. I'm not going to talk about that, but these are 3 problems. These are 3 problems because the training part uses the forward algorithm used in the solution of this problem and similar backward, and therefore it trains. Therefore, it is easier to handle this problem first, and then this problem because this is recognition, using recognition. Then the training problem which uses this and see something. Now, I am not going to tell the mathematics of this. These slides are here, but I am going to skip them. There are actually YouTube videos of the talks here, videos. You can go and look at this. This I can paste it later. Also, there are a series of half-an-hour videos on HMM, maybe a dozen of them. Any question up to this point? I know it's become a little heavy. Let me look at the time, 12:35. So I'm going to cross 1 o'clock definitely. Therefore, what I need to also talk about the language model. Therefore, I'm going to quickly, I'm going to skip the maths part, and I will let you look at the YouTube film. It is there, the maths I'm just going to. The forward algorithm that I talked about is an iterative algorithm. Initially, you start with some approximate values and then do some recursion so that it follows the gradient descent algorithm that Professor Umesh talked about it earlier, so that our model fits the training data well. Does it fit the test data, unknown data? We don't know. But at least it recognizes the training sentence as well, so you can do the training in an iterative manner. Its computation complexity is n square t, where n is the number of states, which is 50 phonemes into 3 states, 150. then capital N is 150 states, capital T is 250 feature vectors. This is a few millions can be done. And Viterbi algorithm is to find the boundaries where we do a maximum instead of the summation. It's computationally easy. So you can, it is similar to the forward algorithm, but you can find out the phoneme sequences and their boundaries. So Viterbi algorithm is also given here, initialization, some recursion and termination. And the optimal state sequence or optimal equivalently optimal phoneme sequence or optimal word sequence. What was spoken in the speech signal can be output here. And the third is training. It uses a similar iterative algorithm. The iterative algorithm is called EM algorithm. E is not estimate, it is expectation, because it uses statistical phenomena of computing the expectation of a quantity of the random variable given the probability distribution. E of x is mean itself, E of x square can be used to compute variance and so on. So expectation and maximization of the likelihood that this model represents the training data well. That likelihood, it tries to maximize it in an iterative manner, go back and forth. I'm not going to talk about that. So you initialize the model. There are two steps. One uses the expectation and other uses the re-estimate the parameters AB pi so that the likelihood is maximized. Likelihood of the new parameters representing the training data is better than the likelihood of the old parameters. And you keep doing it several times, sometimes 50 iterations, sometimes 10 iterations, sometimes people go to 100 iterations and so on. So this algorithm is also called forward backward algorithm. For some reason, it was proposed, it was explained very well in an article by Baum and Welch. Therefore, it's also called a Baum-Welch algorithm or BW algorithm, capital W, forward backward algorithm. I'm going to skip that. The forward backward algorithm details are here. I'll skip that because that's mass. It's there in the slides which will be made available to you. It's also there in the YouTube. Okay, skip. You can estimate the parameters AJ new and so on. Similarly, new values of mean and covariance matrix can be estimated. Expectation maximization of the summary is here. Just take a 10 seconds break. Okay, so let's assume that, we will go through that later. And in general, the models are left to right. If you see the HMM model, always arrows went from left to right because time always goes from left to right. If you say the word mera, it cannot be rame. No. Ma comes first, then sound A comes, then R comes, then R comes. So they say order, time always goes from left to right. Therefore, the phone sequence is also MERA, not any jumbled order. Therefore, even the corresponding state sequences are also from left to right. And there are other versions of the distributive model. There are issues that is involved. Your likelihoods, we compute likelihoods, probabilities are between 0 and 1. You multiply several likelihoods, probabilities values become extremely small. It becomes very small to be represented in finite precision computers. Therefore, instead of computing the likelihoods or instead of maximizing the likelihoods, we maximize log likelihood. Because logarithm is a monotonic function, therefore maximum likelihood is equivalent to maximizing log likelihood. Therefore, you see this term log likelihood in the output of your Kaldi. Kaldi logs are there. You will see term log likelihood. We can use now. I'll spend 15 minutes on. I'll take half an hour more than what is allotted to me. I'll go up to 1:30 probably. I'll try to finish it quickly. I need to do two parts. One, relate this with the Kaldi model that we are going to train today, and two, usage of the language model. So I need 15 minutes for the relation to the Kaldi and maybe half an hour for the language model. So I'll go up to 1:30. Allow me to do that. And our practice starts at 2:30. That was okay. Now we'll come to the Kaldi, our actual toolkit that we use to train. You see the word Sphinx train here. Sphinx was the more toolkit developed at Carnegie Mellon University. That was around 1970, 1987, 88, 88, 89. I was there, and the Sphinx had just been out, and in 88, 3 decades ago, we built the first multi-speaker continuous speech recognition. So Sphinx was popular because that was the first publicly available one. Then there was a HTK, which was a commercial system, and then it became, now it is a free open source tool. Now Kaldi is more popular. Now, of course, wave-to-wave kind of models that Xstep is proposing would probably become more popular with the time. But Kaldi is still useful, HMGM is still useful when you have finite amount of data. Therefore, that's why we are learning to use the Kaldi toolkit in the first few days, because resources are fewer, so we may continue to use the Kaldi toolkit, at least in case of languages where linguistics are fewer. Okay, Kaldi trains HMMs. It trains GMM-HMM. The simplest model, if you have 50 phonemes, then it trains 50 GMM-HMM for each of the phonemes. Each HMM consists of 3 states, except silence also taken as a unit. It has 5 frames because silence can have many kinds of noise, too much variation. Therefore, it is slightly treated as special. But all non-speech silent frame phones are treated is modeled with a 3-state HMM. So if there are 50 phonemes, there are 50 HMMs. They are also called subword because phoneme is part of a word. One word consists of several phones, therefore part of a word could be phone. So we are treating subword HMMs, essentially phoneme HMMs. 50 HMMs correspond to 50 phonemes. They are also called monophones, one phone. So we can train it, and well, there are details of that. So these are also called context-independent phones because there are 50 phones. If the vowel E model that doesn't bother about what is left phonetic consonant, right phonetic consonant, that will come to that later. There are only 50 models, 50 phones, so they are called context-independent. And then we can also train the context-dependent phones. We saw that the vowel A in Puram or U, it depends on the left phone and right phone. Therefore, we can train context-dependent phones and reduce the number of states to improve the computation, to reduce the computation complexity, and so on. How do you train 50 phones, context-independent phones? You suppose you have a sentence. Now we have it. Let's say we have lots of sentences. We downloaded around 1,500 sentences yesterday. Each sentence has the corresponding phone sequence, word sequence. For example, the transcription of, let's say, consider the first sentence is show all alerts, 3 words. The transcription sequence is 3 words. If you look at our transcript, there are some 20 words or so. In this case, 3 words. So the sentence, the HMM corresponding sentence can be composed, can be seen as the sequence of HMM corresponding to HMM. HMM corresponds to the first word show, and followed by optional silence, followed by the HMM of the word all, followed by optional silence. Optional silence, there's a bypass here, and HMM of the word alerts. So I can say this as show all alerts, or show all alerts, or show all alerts. So there could be silence between the words, so it is modern like this. So one HMM corresponds to the entire sentence is the sequence of the 3 word HMMs. Why 3? Because this transcript is 3, this is known to us, and with the optional silence model. Now let us look at the word itself. Let us look at the word show. Although it has 4 letters, it consists of only 2 sounds, 2 phones, sh and o. The sh HMM, which has 3 states, and o HMM has 3 states. Alerts, again similarly, belong to that. Now, look at the show sound, the word show. It is consisting of 2 sequence of 2 phones, S, H, and O. SH itself has 3 states. That's what we are doing. Each phone is represented as one HMM consisting of 3 states. SH has 3 states, O has 3 states, and next word is all. A has 3 states, and L has 3 states. There is optional silence between the words. And similarly, alerts has how many phones? 1, 2, 3, 4, 5. 5 phones. So you can see that the entire sentence is a long HMM which consists of around 20 states. So, point I am making is you can construct HMM not only for the phones but also for the words, because words are sequence of sounds, and also for sentences because sentences are sequence of words. So we can construct a sentence HMM for a given wave file. It is also called finite state network, FSN. It's a sequence of states, about 20 states here, and there are finite states, number 20, that's why it's called a finite state sequence, and it's also called a network because you can see the kind of networking that's happening. Why am I talking about this? Because yesterday some people had a problem in training the language model. They called G.FST, capital G.FST, finite state transducer. FS stands for finite state. It corresponds to this kind of sentence HMM. It's called transducer because it is used in given the observation sequence. It outputs the best phoneme sequence and the word sequence. That's why it's called transducer. But FS stands for finite state sequence, like this, correspond to each phoneme. Okay, we need to train the subword HMMs, which is our phonemes. How do we get the initial parameters? Here is an example of doing that. Let's spend 3 minutes on this. Let us say our first sentence is Mera Bharat Mahan. So this is the transcription. So not only do we need the wave files, but also need the transcription at the word level. It's called a dot trans files or something. In addition, we also need a lexicon file which tells how each word is pronounced. What is the corresponding sequence of the word? The Mahan is the final A is not pronounced. In Bharat also final A is not pronounced. Kannadiga will probably pronounce it Bharata. Even A is pronounced, but in Hindi it is not pronounced. Therefore, this lexicon or pronunciation dictionary is language dependent. Even the word sequence is language dependent. So to train an HMM, we need 3 linguistic resources. First, wave file. Second, corresponding transcription as a sequence of words in some script. It can be Devanagari script also. And third is the lexicon or pronunciation dictionary, which tells for every word that occurs in the transcription, there is at least one entry which tells how that word is pronounced as a sequence of sounds. And these are the labels that is used by Indians. We have Professor Umesh talked about the common label set yesterday. That is derived by a consortium since a couple of decades that has been standardized. Therefore, the phoneme HMM sequence corresponding to this sentence has 16 phonemes. Why? Mera has 4, Bharat has 5, Mahan has 5. 5 plus 5, 10 plus 4, 14, and silence at the beginning and at the end. So 16 phonemes. Corresponding to 16 phonemes, each of them is modeled by 3 states, therefore it is a sequence of 48 states. Now, let us assume that this word Mera Bharat Mahan wave file is duration 1 second, and then there will be 98 feature vectors, approximately 100, but because frame size is much more than frame shift, there will be 98 feature vectors. Just take it for time. So these 98 feature vectors have to be assigned equally. To begin with, we'll assume that the duration of all the phonemes are equal. So 98 feature vectors will be assigned to 16 phonemes equally. So each phoneme gets about 6 feature vectors. 2 feature vectors are extra, you assign it silence here and silence there. Now, therefore, by making this assumption that all the phonemes are equal duration, now we know that this M has got 6 frames. Similarly, this A has got 6 frames. This A has got 6 frames. This A has got 6 frames. In this sentence, the sound, the vowel phoneme A has occurred 3 times, and E, therefore, there are 6 feature vectors from this token occurrence of the A. This is the second occurrence of the A, another 6 vectors, another 6 vectors. Therefore, the vowel A is associated with the 6 into 3, 18 vectors. Sequence of vectors. What we can do is, this sequence of 6 vectors is split up into 3 parts. Take the first 2 vectors, assign it to state 1. Take next 2 vectors, assign it to state 2 of the vowel A, and similarly, last 2 vectors to state 3 of the vowel A. Do this here and do this here. Therefore, for the first state of A, we get 2 vectors from here, 2 vectors from here, and 2 vectors from here. For the first state of A, we totally got 6 vectors. We can compute mean and variance. Our normal distribution is ready. Our Gaussian distribution is ready. And now this is with respect to one sentence. You will take training data, there will be thousands of sentences. Take all occurrences of A and build an initial model for 3 states of A. Do this for all the phonemes, and so that is graphically shown here. We initially assume that all are equidistant, and then the training algorithm will adjust the boundary so that the likelihood of the parameter for the training data is increased. Just rushing to that, and that is the re-estimation of parameter. Embedded re-estimation, speech dynamic signal, therefore it is context dependent. If you look at the oval, this is what? Tiruvantapuram. This is U here and Puram ka U here. This variation depends on the context. Therefore, it is better not to treat oval U as just one, but oval U preceded by R. This is Tiruva. U, R. Preceded by R and followed by Va. Tiruva. You treat it as a separate unit. Now take 50, there are 50 phonemes. Take one phoneme, in this particular case, U. U could be preceded by any of the 50 phonemes on the left side, and U could be followed by any of the 50 phonemes on the right side. Therefore, we can in principle have 50 left context and 50 right context independently. Therefore, we may model 50 into 50 versions of the same oval U, because 50 left context, 50 right context. Now this we can do it for each of the 50 phonemes. Therefore, we need not have only 50 HMMs, but 50 cube HMMs. These HMMs represent context dependent phones. If it is context independent phone, we call it a monophone. There is only 50 HMMs correspond to 50 phones. If we take into account left context and right context, then we call it as a triphone. There are 50 cube triphone models. If the number of phonemes is a capital N, there will be capital N cube phoneme models, and they are called context dependent models. Therefore, there will be N cube triphone models. And in Kali, we are going to train triphone models also. And context, right? And that's what is shown here. If N is equal to 50, each HMM has 3 states. Therefore, the number of states could be 50 cube into 3. which is 3 lakhs or 4 lakhs. And to estimate the parameters of the 4 lakh Gaussians, we require large amount of data. But kya kare, my language is Adi or some such language which has very little data. Therefore, I can't estimate the parameter of 4 lakh Gaussians. Forget about Gaussian mixture model, even Gaussians I can't train. Therefore, I need to reduce the number of Gaussians, and the number of Gaussians can be reduced by using technique called state tying, which uses the decision tree. Example of decision tree is there. So the number of Gaussians are reduced by so from 4 lakhs, it's reduced to 10,000 or 1,000 or 2,000, depending upon the amount of speech data that you have. So, although there are 4 lakh states, triphones, 4 lakh states correspond to 50 cube triphones. We require 4 lakh Gaussians, but we have only 10,000 Gaussians. So sometimes we copy one Gaussian to several states whose properties are similar as per the acoustic property is concerned, and that is called state-Shannon mapping. Shannon is a term that you may hear. That is a shared state, shared phoneme. That's why it's a shared emitting Shannons. This is Shannon is a term. Okay, so you can reduce from 4 lakh to just from 20,000 also. So in Kaldi, we start with the training monophone models. How many are context independent models? How many are there? 50 approximately. Then we train triphone models, context dependent models. How many are there? 50 cube in principle. Not all 50 cubes do happen. It will be number less than that, but it will be thousands, several thousands and 10,000s and so on. They are all characterized by 13-dimensional MFCCs. Now, we do some more. So this model is called triphone model. There are other sophisticated triphone models. Therefore, this model we call it a tri-1. So when we train HMM today using Kaldi, we have some results for the monophone model. It will not be that good. Word error rate will be high. Then we go to tri-1 model, which we are into the phonetic context. Accuracy increases, word error rate decreases. Then we are not happy with this. Still, we want to reduce the word error rate. So we go to sophisticated models, so that is called tri-2, tri-3 models. I'll give a brief description of that. What are the features that we use? We use the MFCCs. MFCCs, successive MFCCs are correlated. Therefore, that is not a good feature vector. So we can decorrelate it using principal component analysis, or we can do principal component analysis, a transformation of the 13 MFCCs into another 13-dimensional space. It's a rotation of the vector space material. This rotation or the matrix transformation can be done in a manner that it increases the discrimination between different classes. It reduces the confusion between classes. So we want to do the transformation of the 13-dimensional MFCC feature vectors such that the confusion between sounds reduces. Pa and pa we want to distinguish. So MFCC is not good enough. Principal component analysis of MFCC is not good enough. We do what is a discriminant analysis, linear discriminant analysis, which increases the capability. So the transform feature vectors will be able to separate the classes much better, separate the phones or triphones much better. So that is called linear discriminant analysis. There is also something called maximum likelihood linear regression. It sort of helps to take care of differences between speakers. So my head size is longer, therefore vocal tract length is longer, therefore the resonance frequencies are lower. My grandniece is she's short, her vocal tract length is small, therefore resonance frequency is higher. So different people's resonance frequency for the same phoneme will be different. Therefore, the mean vectors of the distributions for the same phoneme for different people would be different. Let me wait. And this can be this speaker dependence of the mean vector mu can be, that effect can be normalized by using what is known as maximum likelihood linear regression. Acronym is MLLR. So in Kaldi, we do the MLLR also. In addition, this MLLR is done in such a way that transformation is done at the feature level, MFCC level. Whereas, if the training data is known, but also if you see the transcription, yesterday's transcription of file had an identity, some ABCD, some digits at the beginning, tab, sequence of words. This is file identity, which also had the information about the speaker. Or speaker number 1 spoke the sentence number 13, and so on. So the files may even be associated. During a training, we know this 100 files are spoken by speaker number 1, next 17 files were spoken by speaker number 2, and so on. So the first 100 files have similar speaker characteristics, therefore it can be normalized. Speaker normalization can be independently of the first 100 speech files belong to first speaker, and the next 17 files belong to speaker number 2 can be, the speaker normalization can be done independently. Such speaker dependent training is called speaker adaptive training, is called SAT, which also does the vocal tract length normalization. So if you do linear discriminant analysis and maximum likelihood linear regression through the triphone or context dependent HMMs, such a model is called Try2. Kali does that. In addition to LDA and MMLR, you also do the SAT, speaker adaptive training. Such a model is called Try2. In our script, I saw that we are going to train this, we are going to train this, and we are also going to train this, but get the decoding only for this model because this will be similar. So we get 3 word error rates, high word error rate for monophonal context dependent because there are only 50 phonemes and HMMs. When we model the context dependence, try one, our word error rate decreases. When you use a sophisticated model which uses linear discriminant analysis, maximum likelihood linear transform, and speaker adaptive training, we get even more better model. It's called Try3, word error rate decreases further. Okay. These are the 3 numbers that we are going to see earlier. Just to give me a minute. Professor Rao, I am in a class. Can you call after 1 hour? Thanks. Sorry. Okay, so this is the Kaldi part, and so that is what we are going to do. And I'm going to, this is still in HMM, GMM. HMM involving GMM, and tomorrow Prasanna sir will introduce the neural network part. He will talk about the deep neural network, and HMM GMM is the model that ruled the roost till about a decade ago, but it makes lots of assumptions. See, there are six assumptions I have listed here. They're all making. So there are assumptions that successive observations are independent and so on. It's not good. Whereas HMM DNN, when the GMM is replaced by deep neural network, some 2 assumptions are not necessary. Therefore, model becomes better. When you use a recurrent neural network with the connectionist temporal classification, only 1 assumption is necessary. When you talk of encoder recorder that Professor Umesh talked yesterday, none of these 6 assumptions are necessary. Therefore, the performance increases. This is just a peek into the glimpse into the future. I am not going to talk about that. So I will take a break here because I just now I talked about the how to relate, what kind of models are we going to train today afternoon. Now I will go to talk to the language model. Therefore, I will take 1 minute break. Okay, there's a question. 13 into 9 MFCC means, sir? 9 is what? No, there are 3 states for each HMM. Therefore, each state would have 1 distribution. and one distribution in the 13-dimensional vector space. Therefore, it will be one mean vector of 13-dimensional vector space. Okay. This question of Mahesh is in context something else probably. I'll wait for a, I think we need a break. I need another half an hour. We'll take 2 minutes break. If there's a question, please feel free to ask. I'm available.
So there is a question in the chat box.
Yeah, I didn't understand that question. It is 13 into M MFCC means, sir. I didn't understand the context, therefore.
Sir, in your slide, sir, in your class, whenever you shown that try 1, try 2. Yeah, this slide, sir.
Sorry, try 1, try 2. Sorry. Okay,
yeah. I think next. There in 3 model are there. 3 try mono try. Yeah. In this slide, you have written that 13 cross 9 MFCC. So in this, try 2.
Why did I do that? 13 cross 9 MFCC. Okay. When you do the linear discriminant transformation, you do not take only 13 MFCC of the current frame, but 30 MFCC of the previous 4 frames and later 4 frames. So totally there are 9 frames. There is 13 into 9 feature MFCCs. So 13 into 9 is 117. So 117 feature vector is transformed using a linear discriminant analysis to 40-dimensional feature vector. There's a dimensionality reduction here. Thank you. Okay, thanks. Okay, our break is over. Let's continue. It is 1:10 already. So I should try to finish it in 20 minutes, but let's see. Language model. Speech is not any other signal like the geo signal or ECG, EEG. It is spoken language. Language is involved. It is not just an acoustic signal. Therefore, the language has its own language constraints. Therefore, not only do we have, when you talk of model, not only do we have an acoustic model, but a model that describes the linguistic constraint of that language. Language model is language dependent. So this box now has 2 parts. So far we dealt with the acoustic model, GMM-HMM and various things, but there is a language model also. And also even the testing part, there is a matching of the observation vector sequence with the acoustic model. That gives probability of various phoneme sequences. From the phoneme sequences, the Mera Bharat Mahan, the sentence hypothesis is done by matching the phoneme sequence possibilities and associate their probabilities with the language model. We'll have a quick brief look at that. Okay. Each sentence is a sequence of phonemes. So we already looked at that, but not all phone sequences are valid words in language. Lexicon determines that. For example, in English, M-A-N, man, is a word, but is not a word. This could be a word in Mizo language because the words can begin with and such as words. There is a sequence. Syntax, grammar, we already know that this is a word grammatically correct sentence. This isn't. Therefore, all possible word sequences are not grammatically correct. Therefore, there are probabilities of the word sequences that are valid. Of course, when you do the speech recognition, speech understanding, we also have to look at the semantics. Flies can mean verb. It is a noun here, meaning could be different. That's it. How do you combine acoustic model and language model? Let us consider an acoustic feature vector sequence. So our Mera Bharat Mahan is 250 frames long. So it is a sequence of 250 feature vectors. we call it O1, O2, O250. Here he calls it a small y1, small y2, small y50. So collectively he calls it capital Y. Our given an observation sequence of 250 feature vectors. Our goal is to find that word sequence, it's a bold word sequence, Mera Bharat Mahan, such that the conditional property of the word sequence is highest given the observation. Given the MFCC word sequence, the probability of the Mera Bharat Mahan sequence of 3 words is highest, and that we will output it. So we want to find the word sequence which maximizes this likelihood condition problem. Now, base rule says that it can be written like this, and therefore it can be written like this. Let's look at this equation. Now, in the numerator, this term has been split up into 2 parts. One is probability of word sequence itself. Probability, what is the probability that the Mera Bharat Mahan is grammatically correct in Hindi language? What is this? That is given by the language model. Language model gives the probability of the word sequences. Therefore, this can be computed. Take large amount of text. We don't even need speech signal. Take large amount of written text. Plenty of them available in the internet. Find the probabilities of the word sequence. Language. Probabilities of the observation given a sentence or word sequence, this is given by the HMM. So this can be computed, and probability of the observation sequence itself, that is constant in the maximization, quite often is ignored. Doesn't matter, because we are want only the maximum over the word sequence, and probability of Y doesn't depend upon the word. Therefore, maximization, this term can be ignored. Therefore, all that we need is this term and this term. This probability of the word sequence is given by the language model. Probability of the observation given the word sequence is given by the acoustic model. In our case, GMM. We need to find the probability product of these probabilities and find out that word sequence which has maximum numerator. So when you want to find out, we have to search over all sequences of words, and therefore that is a hypothesis search. So continuous speech recognition of continuous words, essentially has 3 parts. Compute the likelihood of the word observation sequence given a word sequence, multiply by the probability of word sequence given by the language model, and then you compute this product for one word sequence, compute it for all possible word sequences. There are infinitely many, lakhs, millions of them, and find out that word sequence which has the highest probability. Okay, we already looked at this. Each sentence is a sequence of words. Each word is a sequence of phonemes. Each phoneme can be modeled by HMM, which is a sequence of states. And each the word is a sequence of phones, and that information is given by the word model. And the sentence is a sequence of words, and language probability is given by language model. Here it is a trigram. We will come to that later. So these things can be computed. Pronunciation dictionary, that we already looked at it. The word, for example, aage has vowel a, ja, ga, and e. Ignore the VBs. And Abbas, the person's name, a, and some BB. This is the pronunciation dictionary lexicon. We have already looked at that. Sometimes one word may be pronounced multiple. The Hindi word corresponds to the English word science is Vigyan. Vigyan Bhavan in Delhi. That's how it is pronounced in Hindi. You go to South, even Maharashtra, they call it as Vigyan. It is because in Sanskrit, that is how it is pronounced. So the word, one word may have multiple pronunciations. If there are words or multiple pronunciations, you have to put it in there. And yesterday when we saw the lexicon, somebody asked why A has 2 entries, but because the word A can be pronounced as A or A. So that's that. Now, reasons for pronunciation variability, forget it. You can represent a word as a network of phonemes, and that can also take care of the pronunciation variabilities. We can look at that. And various probabilities, if there are multiple pronunciations. For example, this is the word 31. 31 or 29? 29 probably. 21. 21 or 31. So if it is 31, 31, 31 or 31. Well, both pronunciations are possible, and multiple pronunciations that these probabilities of the multiple pronunciations can be estimated from a large amount of training data. Therefore, that can be done. What now I am going to do is to give an example of how a language model is used to output the best sequence of words or to hypothesize the best sentence. So our input is MFCC feature vector sequences, and acoustic model will give the phone the probability of various phones occurring at various times, at various frames. From there, we use the linguistic information to hypothesize the best word sequence. So the generation hypothesis can result in the one single sequence of word Mera Bharat Mohan, which has the highest probability, or collection of the n best word sequences Mera Bharat Mohan, Mera Gaon Mohan, or Tera Gaon Mohan, and some such thing. So these are infinite word sequences. What are the word sequences which are the highest top 3 probabilities? That is useful. You will see that in practical implementation, these will be useful. Or it can also give overlapping word hypothesis in a lattice, word lattice. Let's quickly look at that. Our goal is to find the path with the least cost. We will talk about this later. Here is a graph. There are lots of lines. Time is along the x-axis. And each line corresponding to one phoneme. The silence phoneme is at the top, and all other about 50 phonemes are alphabetically arranged. I is here, E is here, and the last one is W, alphabetically arranged. This line, thickness of this line shows the probability of the phoneme SIL, silence, at various time instances. Obviously, something was spoken, and at the beginning there was silence, at the end there was silence. Therefore, the probability of the silence phoneme is very high for the first few speech frames. And the probabilities of the likelihoods, likelihoods of these phonemes initially is small. But after some time, the likelihood of silence decreased, likelihood of became little bit, and likelihood of W became higher at this particular point. So you can see that at various time instances, various phonemes seem to have higher likelihoods, as shown by the thickness of the line. So we can sort of traverse through this graph and look at the phonemes which are high probabilities, and therefore this phoneme occurred in this duration, and so on. We can make that guess. Let us look at that. The probability of silence was very high for some time, and it decreased. So in this time instance, this silence has some probability, and this also has some probability. Therefore, the silence could have occurred from this time to this time. I have shown it here. Silence could have occurred in the first few frames with high probability up to here, and with decreasing probability up to here. It's likelihood actually, condition probability. But this duration, the likelihood of silence is medium, and likelihood of W is also medium. You see here, W here. Or I is also there. It's also there. So this time interval from here to here, there are 3 competing phones, silence, and W. They have significant probability, others are extremely small. So let me just see whether there is any phoneme. This question I will talk about it later. So at this time interval, silence can occur with some probability, some significant probability, W and A. Therefore, there are 3 phonemes that are possible at here. But at this time instant, only W has very high probability, significantly high, more than half. Therefore, definitely W has occurred, and so on. this point, again, either it would be a or o. You see a spoken by a South Indian versus a spoken by an Assamese. Oh, there is a round there. So it could be a spoken by a South Indian or o spoken by a Assamese. And there's an n here. So you see that this probability is given by the acoustic model can be displayed in this manner, and the probabilities of various phonemes and their tentative time durations can be plotted like this. Now we will use the lexical information. Suppose we know that a person is speaking the PIN, 4-digit PIN, OTP, okay, or PIN, OTP, let's talk 4-digit OTP, then the numbers have to be sequence of digits he's speaking. Then this has to be one of the digits. Then this has to be WAN. W1 is written as O, one is, okay, O-A-N, 1. Although it is written as O-N-E, it is a sequence of W-A-N. Whereas, suppose this sentence was spoken in the context of a cricket match, then the person must have told our team won the match, won. One is pronounced again as W-A-N, there's ambiguity, or W-O-N, on. Bengali speaking on or something. So in each case, this path could be there. So by looking at any given point in time, there could be multiple words that can be competing. In this particular case, it could be the digit 1, O-N-E, or the word W-O-N. So both are possible word contenders, word candidates in the first part, only this part. Then there will be others and so on. So the point I'm making is, starting with the likelihoods provided by the acoustic model, HMM, we can guess the phonemes at various time instances and tentative durations. And using the lexicon, which gives us how different words are produced, we can guess the word hypothesis. In this particular case, from time instant from here to here, either the word one is there, single, one O-N-E, or the word W-O-N is there. Here is an example that I am taking, that at this point instances, the word could be take, or Kate, or they, or K. K and Kate. Ta is not pronounced, therefore K and Kate sound similar. Therefore, this is the 4 words are candidates from the time interval around 30 to 50, and their tentative durations are shown, and then there are other words popping up at other time instances and so on. So we started with the displaying of the acoustic probabilities provided with the HMM to phone hypothesis or phone lattice to word lattice. Here is a word lattice. Word lattice, I am talking about various possibilities there. This has a higher likelihood than this and this and so on. And this is, I take it from Ravi Shankar's PhD thesis in 1996 at Carnegie Mellon University. And you can see that various words are possible. Now, which word should I take? Should I take the word Kate or K? Both are lexically possible. But this is where the grammar comes into picture, lexicon, syntax comes into picture. If you look at the sequence of words there, what are the probabilities? Then the best word sequence would be take Fidelity's case as an example. So lexicon helped us to give up to this, and the grammar helped us to derive this. Just check the time, 1:27. I need to wind up quickly, and this can be the best word sequence can be computed using what is a directed acyclic graph. Computer scientists did that, and when you do that, there can be multiple hypotheses again. Semantically, this is fine. It is hard to recognize a speech, but this is semantically doesn't make meaning to recognize which Professor Mees talked about that yesterday. Then, how do you represent the syntax? I will take 10 more minutes. How do you represent the syntax? We can use the traditional linguist model, but that is cumbersome. So, or you can put it in the form of a network. It's called Gaussian form. In a specific task domain, this is useful. I'm spending 1 minute here because many of us will not have a large amount of data to train the model with the 10,000 hours of speech. We build a model with 50 hours of speech, or even 50 hours may be difficult and things like that. And therefore, we may, if you want to build an application, we'll build an application for a very specific task domain to recognize spoken OTPs or to recognize the PNR, sequence of digits, and so on. In this particular inquiry in a railway reservation counter, you may make a mobile call to the railway counter and speak sentences. So in specific task domain, this kind of grammar can be useful. But now, that is okay for a specific task domain. When you do the Google voice search, you ask any question, any continuously. Therefore, our model syntax should be task independent as far as possible. We should cover all words in that language. And this is where we use what is known as an n-gram, and I'll spend 5-10 minutes on that because in Kaldi we are using n-gram. Let us consider, so what is that we want to model? We want to model the probability of word sequences. Let there be I words in the word sequence W1, W2, Wi, and we know that by chain rule, probability of the word sequence, this one can be written as the probability of the first word that has occurred, and the conditional probability of the second word occurring given that the first word has occurred, multiplied by the probability of the third word occurring given that the first two words have occurred, and so on. Now, this word, now if you want to compute this for, let's say, word sequence, one sentence may contain 20 words, then there will be 20 such probabilities. These probabilities are difficult to compute. Therefore, what we will do is, we will not compute these conditional probabilities for the long word sequences. We will say that probability of the third word depends only on the previous two words and does not depend upon the much past history. Such a grammar is called trigram grammar, because predicting the probability of a sequence of 3 words, W1, W2, W3, we need to know the probability of word 3 given the previous 2 history. So there are 3 words involved. Therefore, this is called a trigram. A grammar estimating the probability of a sequence of 3 words. So it has a finite history. That's also called a Markov model and so on. We'll ignore that. Now, we can make, even this may be difficult. Why? Think of a language such as Hindi or Kannada or Tamil, whatever it is, there may be lakhs of words. So how many such probability values will be there? 1 lakh is 10 power 5. There are 10 power 5 into 10 power 5 into 10 power 5, because first word, it's a sequence of 3 words. First word could be any of the 10 power 5 words. Second word also could be any of the 10 power 5. Third word also any of the 10 power 5. 10 power 5 into 10 power 5 to 10 power 5, 10 power 15. Hey, this is billions and trillions and so on. We don't have that much text data. Therefore, even this is difficult. So can we make a further assumption that we'll use only one finite history, therefore we compute the probability of word sequence of only sequence length 2, then it is called a bigram, 2 words. Probability of the word 2 given the knowledge of one past is called bigram, and this is called unigram. What is the probability of one word occurring in general? Suppose you take the word English, Hindi language, the word mera occurs much often than samudra. Samudra probability will be extremely low. So you can compute the probability, a priori probability of each of the words is called unigram. Given a large amount of text, this is easy to compute. In fact, then you try to compute bigram probability, you try to compute trigram probability, and in general, so this is also called 3-gram. If you compute the probability of the sequence of 4 words, it's called 4-gram. if you see the ASR challenges, people use 5 gram and so on, using large amount of data. But in the Kaldi that we are going to do today, we will be using trigram or n equal to 3 n gram. The estimation of these properties can be formalized. Here you can compute it as the ratio. You can estimate the properties as the ratios of the counts of the subword sequences. I'll skip that, but there will be, as I said, there are 1 lakh words in the Hindi. Therefore, there will be trillions of probabilities that you need to compute. Some word sequences may not occur in the training data, but it doesn't mean that it will not be spoken by somebody else. Therefore, some probabilities of the word sequences, probabilities of some word sequences, although they can legally occur in the sentence, might become 0 because that word sequence did not occur in the transcript of the training data. Therefore, we need to do some robustness, and that is called discounting. But I'll skip that. But what we'll do is we'll stick to the n gram. What we can do is the following. Suppose instead of depending only on the trigrams, we'll estimate the trigram probability as a linear combination of trigram probability, bigram probability, and unigram probability. It's a linear combination. This lambda 1, lambda 2, lambda 3 has to be determined, but that can be estimated for giving the best performance over for the training data. Of course, there are constraints are there. That is called linear interpolation. There is one more option. We won't do linear interpolation, but if the trigram probability is there, use it. If the trigram count is greater than 0, just use this. If trigram count is 0, that word sequence didn't occur, then you use the bigram. If the bigram is also not available, then go to the unigram. So this is a non-linear method of estimating the n gram. So this is called back off. In American English, back off is going back, reverse. So if the best estimate is not there, go to the next best estimate, and so on. And backup grammar, the algorithm for backup grammar is shown here, sort of. If the trigram probability information is there, compute. If the trigram count is there, compute, estimate the trigram. Otherwise, go bigram. Otherwise, go to the unigram. And there are some nuances there. That is okay. So that I completed my 135. So let me give me a couple of minutes to conclude. This is a summer school on speech recognition and automatic speech recognition using Gaussian mixture model in conjunction with hidden Markov model. That is what we learned to model the acoustic model. And language model, that is here, we talked of n-gram and back of n-gram. And in this particular case, we learned up to trigram. And in speech recognition, there is a acoustic model here, there's a language model here, and then there's a search. In fact, this search concept comes when you want to optimize your systems, but we'll not talk about that. So we dealt with the one type of acoustic model, one type of language model, n-gram language, one type of acoustic model which involves hidden Markov model. And we have seen earlier, yesterday Professor Umesh also gave it on various other models involving neural networks. Professor Umesh and others will talk, sorry, Professor Prasanna, Deepak and others will talk tomorrow about those models. So thank you for listening, and I took the 40 minutes extra. If there are questions, we'll take it up. Otherwise, we'll take a break for the lunch.
Yeah, thank you, sir, for the insight. Sir, I have a query, sir. In the Kaldi, like once the step is we generally do at phone level. After phone, we get a word, right? So for all these cases, there'll be a posterior probability, right?
Yes.
Yeah. So how to get the posterior probability at word level, sir?
If you can get the posterior, what is word? It's a sequence of phonemes. Therefore, if you compute the likelihoods of the phoneme sequence, then likelihood of the language model of the a priori probability of the phoneme sequence language model, you can use the base rule to compute the posterior probability of word sequence. The base rule applies whether it is state or phoneme or word or sentence, it doesn't matter.
Yes, sir. Actually, my concern is like there will be too many pronunciations. I mean, there will be multiple pronunciation for each word, right? So, based on the input signal, I mean, signal, the accent will be varying. Right? Assume take an example of a Telugu speaking guy. There are three accents, right? So, which one should be picked? So that is being estimated by the posterior probability, right, sir?
So the maximization, the search will determine.
Okay. So you mean to say
big search.
Yeah, big search. So that is again a conditional probability.
Yes.
So based on the search, it will go.
Yes.
Okay. Understood. Thank you, sir.
Yeah,
Thank you.
Yeah. There are two questions. I will have a quick answer to that. One is for a language not having any script, how to create a transcription. Okay. Even if you do not have a script, okay, but you still speak, the sound sequences are known. You can use the labels for the sound sequence. Whether you use Roman script for the labels or the Devanagari script, it doesn't matter. Roman script is easier because programs do that much better. But so the pronunciation label can always be done as we did here. And we have a label for the sounds used by the Indian language in general. It is better to use that because you may have very little data. So if you are Adi language, you have only 5 hours of speech data, but there is 50 hours of speech data for the, let's say, Tibeto-Burman language, another Tibeto-Burman language. You want to use that, or the neighboring state, Assam, Assamese, you want to use that. In which case, using a common label employed by other researchers would be helpful. So script doesn't matter. It's just that you write it in either, you stick to Hindi Devanagari script or you stick to Roman script, fine, no problem. Next question, pronunciation lexicon are one and same? Yes. Lexicon is the list of the words and pronunciation dictionary is corresponding list of words, how it is pronounced. That is written as a sequence of labels as it is shown here. Even if you go to the dictionary, online dictionary, they'll give you the word, how it is spelled, and they also give you the sequence of IPS symbols to be how to be pronounced. Sometimes these days even there is an audio file, you click on that, it will play it out. So lexicon and pronunciation dictionary are synonyms. Okay. Any other questions? Good. So we have covered the essential parts of the speech recognition for that is sufficient for today's practicals. On that basis, thank you for your attention and questions. I appreciate questions that we can interact with others one way, especially in the online mode. Thank you for all of you, and probably we meet at 2:30 for the practicals. Bye.
Yeah, thank you very much, sir. And thank you very much for participants. We will gather again at 2:30. Thank you.